Okay, I think that's coming through YouTube now, isn't it? We can see.
Yeah, the YouTube's working now, Josh.
Perfect. Okay. All right. So good morning. I think we'll make a start. Welcome everyone, and thanks for joining this Introduction to ioGAS webinar. The event is co-hosted by the Early Career Network of the GeolSoc, as well as the Early Career Professional Committee of the SEG. We've had a fantastic response to the event with over 820 registrations. So given the limited capacity of our Zoom account, we're also live streaming the event on YouTube Live. Throughout the session, please feel free to use the chat functions both on Zoom but also on YouTube Live to ask questions. Hugh from the SEG and Matt from the GeolSoc will be keeping an eye on questions as they come in, and we'll have a number of breaks scheduled throughout the morning where there'll be an opportunity for James to answer some of your questions directly. So I'd just like to say a very big thank you from us to James and Dave for their willingness in putting together today's event. And I'll hand over to James to kick us off. Thanks very much.
Thanks very much, Josh, and welcome everyone. Really appreciate the number of registrations and the interest we've seen in this event. I think what you'll get from today is a sense of passion, both from myself and Dave, for this software and its use. And it's great to see the interest in what we can do. I thought today we would kick off with asking Dave to give a talk that I know I've seen a version of previously, but I think really sets the scene for today and really sets the scene about why we want to, as geoscientists, look at data and understand how we can look at the patterns in data and trying to resolve what more we can get out of data sets that we collect. So I'm going to ask Dave to do a talk. We'll then have a small question and answer session after that as well to get a bit of interaction from anyone online. And then we'll go into the main focus of me demoing the ioGAS software. And it will start off with a basic overview. And then we'll go through various functions and some of the kind of cool stuff, I guess, you can do in ioGAS. And then towards the back end of the session, around sort of 12 o'clock-ish for an hour or so, what I want to do is go through some more of the advanced multi-step workflows that allow you to take the sort of typical data sets we might have access to and go through various analytic workflows to show you how you can start to extract better information from the data you have. So I'm going to run it very much as a demo. I think this gives access to more people by doing it this way. There'll be times throughout the day when we can take a few questions. There's a few break sessions where we'll take a few questions at that point, and then a question and answer session at the end. And then we can obviously, there'll be ways of following up with us for more information if required. So this morning, and thanks to Geological Society Early Career Network and the SEG Early Career Professional Group for hosting this, allowing us a platform, I guess, to reach so many of you. And I hope this is showing us a little bit as well some of the ways we're working differently in the current environment with the COVID-19 restrictions that are in place. So I think without further ado, I want to introduce Dave Lowy. I've known Dave for a number of years, back in his previous role of looking after a company called ioGlobal. And this is where the ioGAS software came from. They became part of the Reflex company, which is part of the IMDEX group, I guess, back in probably 2012, was it, Dave? Something like that. And
7.5 years ago.
Yeah, there you go. And certainly from my experience, I've been using ioGAS, I think from very, very early days, 2004, something like that. So this is a piece of software that's been around for a little while now, but always been evolving. And Dave's got a lot of history in this space. So I asked Dave to give one of the talks I know he has, which is really about sorting the signal from the noise. And I think, like I say, this will set the scene for why we want to use software like this and look at our data sets in a different way. So Dave, I'll hand over to you at that point. Thanks.
Yes, thanks, James. And again, just to reiterate, thanks to the organisers for giving us a forum like this to talk about ioGAS and the way that geoscientists look at data. So this, I don't think you won't have heard a lecture like this talking about data analysis in the geoscience. I don't think. It's a slightly different take on it. And this 45, 50 minutes is really about the philosophy of data interpretation. But one point I will keep making on the way through is interactive as ioGAS is and how easy it is to use it to take you to what the signal is. There really is still no substitute for thinking. And just remember that all the way through this talk, please, that you can have very clever tools at your disposal, but unless you're thinking the whole time, you can very easily be led up the garden path. But I'll be expanding on that as we go through. Now, here's a couple of books which I read a while ago now, 6 or 8 years ago, maybe 10 years ago, time flies. But they were really the genesis for me making this talk, which is not technically a technical talk per se. And neither of these books actually come from a geoscience background. So the top one there, The Signal and the Noise, that's where I got the title from this talk, Why So Many Predictions Fail But Some Don't, was written by a bloke called Nate Silver. Nate's claim to fame is that with both of Barack Obama's election wins, he predicted them, where many didn't. He failed to predict Trump winning, though, which is a bit of a speed bump. But right now, just out of curiosity, just for you going a sense of curiosity, he runs a very interesting website doing lots of analysis of data. He has Joe Biden 10% ahead of Trump right now in the US polls. And the other book there, which I really think should be on the undergraduate reading list for all people who are interested in exploration or going into a career in exploration in geoscience, is Fooled by Randomness. And that is a perfect title, I think, in exploration, because often we are fooled by randomness. And I'm going to give you some examples of this as we go through the talk. The subtext there, the hidden role of chance in life and the markets and your exploration program. Nicholas Taleb is a very entertaining writer, a bit of an insufferable wanker, though, while you're reading it. But if you put up with that, he will give you lots and lots of anecdotes as you go through, which you'll be able to relate to your own career in exploration. And it's really a very good idea to think about those continuously. So a little bit about data and what is signal and noise. So just in the geosciences, we are swamped with data, really. And as time goes on, as more sensing equipment gets moved to the point of field activity and work, which we do as a company, IMDEX, we very much promote this, you just will be continuously generating data, but that's not necessarily giving you information, and that's the trick. So when your boss asks you, you've been out doing this sort of work, what was the answer? What does it mean? They're really asking you, what signal did you see? Right? And so that's just another way of thinking about that. And man, when we started working on ioGAS 15 years ago, analytics was actually quite a rare word in the industry. It's not now. So I thought it was also interesting to talk about the definition of analytics. And in ioGAS, the A in the middle does not stand for analytics, by the way, though it could now. And this is just from Wiki a while ago: the discovery of and communication of meaningful patterns in data, simultaneous applications of operations research, stats, and computer programming. But the key point there is that it really emphasizes data visualization. So when you think about that and you think about the term analytics and data science, well, in fact, geoscientists have been into analytics ever since there was geoscience. We've always been going out and collecting data and trying to make different visualizations of it so that we can convey what the signal is, or what it is that we've found from the data, the information, not just the raw data itself. So geoscientists per se, although often we regard ourselves as being not particularly numerate sometimes, we should never think that geoscientists are not into the world of analytics. We all are. Just a comment about signal and noise. So a way to think about signal and noise is that noise is anything in the data that's actually not related to the purpose of the survey. But the purpose of the survey or the task you're bending the data into can actually change with time or change with the use. So another way of saying that is one man's noise may be another man's signal. So just be aware of that. And an example of that might be in an exploration program. If you're doing exploration drilling, reconnaissance drilling, you might be analysing for arsenic in a gold exploration program using arsenic as a pathfinder. You might actually find something at depth turned into an operation, and then downstream a metallurgist actually goes into that database 15 years later and sees the arsenic assays and thinks, thank goodness, now I can work out where the arsenic is deported in the deposit, because we don't want the arsenic coming out with the gold because it poisons the process, for example. So the quality of the data, that raises a whole lot of issues, because when you design a sampling program, you might not have the end use of the data in mind if it's separated in time. So just another thing to think about. It's another reason why it's always good to collect good quality data regardless, right? Because data persists, the interpretations change with time. So what about noise? How can you have noise in the data? How can you make data difficult to deal with? And I will explore some of these later on. But you can induce noise in your data with sampling errors. So things like taking structural measurements. If the core is spun, for example, you will get a whole bunch of dodgy structural readings. If you're out collecting soil samples in an exploration program, if you mix up the soil horizons, often the variation you'll get in, or the variance, the variation in the data you'll induce just due to mixed soil horizons with nothing to do with the presence or absence of mineralization. If you do that, you really, really obscure the signal that you're looking for. You can conceive a program poorly right at the outset. So for example, if you're conducting a lithogeochemistry program and you're looking for alteration vectors, and you take your chips from an RC program or pulps from a diamond program, and apart from the direct assay of gold or copper or whatever it is you're looking for, you might be interested in the multi-element suite. If you send that off for an aquaregia digestion, it is not total for elements like potassium, sodium, aluminium, etc. So there's nothing wrong with the work that the laboratory did, but you asked for the wrong digestion if you want to use that for a lithogeochemical vectoring program. So that's just poor program design, or another way I put that is poor experimental design. Sometimes we also get the sample spacing wrong. I'll come back to that. Often we tend to, especially from a geochemical point of view, often beat up on the labs, but really it's really quite rare these days for the laboratories to stuff up quite badly. Where the most problems come about is the analytical method or some request of the geoscientist was not appropriate in the first place. Now, just some comments about analytics in geoscience. It's actually a process with two streams. And that graphic I'll put there sums up the process really well. And it's not even from a geoscience background. I think that graphic was taken from a network analysis website, I think, looking for faults. But in both modes of operation, both modes of use in analytics, we start with data and we hope to gain knowledge. If we go across the top tree there, we're really interested in interacting with the data a lot and looking at it, visualizing many different ways to see if we can learn something from it. If we learn something that's useful and that's repeatable, then we might build a model from it and we can apply that model to new data when we require it to go straight to the knowledge step. So that's the bottom part of that process tree. Interestingly, when we first conceived of ioGAS and built it, it was very much concentrated on that top flow through the visualization, but now it actually has capabilities in both of those areas, and you'll see capabilities in both of those areas later on this morning when James is talking to you. Just some other comments about data and what is a model and what is an outlier. That is a really simple plot there, but it illustrates a lot of the subtleties around analysing data. Now, if you're trying to build a model, some sort of a process model, if you're talking to a mining engineer or a MET, for example, they would be more interested in the sequence of data without that outlier. They're trying to model that background process, and they would regard the outlier sitting out there as something that's not worth modeling. It just interferes with the model. But from an exploration point of view, often the outlier is the thing that we're actually seeking. So if you're in conversations with people, especially with data science, that don't have particularly very much domain knowledge about what you're trying to do, they may even start to run some analyses for you and throw those data out and you never see them again, when actually that's the data you're looking for, right? So these are why you need to be very careful when you're using some, especially some of the more fancy methods. The other thing about that outlier is it illustrates that if you project all of the data down onto the x-axis, or you project all of the data across onto the y-axis, so you're looking at the data in a univariate way, one element at a time, you don't see it. It's not an outlier. It only reveals itself as an outlier when you plot both of those variables together, a bivariate plot or a scatter plot. Now, what could cause that in an exploration program? What could be the significance of an outlier that looks a bit odd like that? Well, it might be that your sampling program has not hit the mineralization per se, but it's hit a pyrite-rich alteration, salvage around the mineralization between it and the country rock. And with a lot of pyrite around, you get a lot of acid leaching and things like that in a special environment. So it perturbs the signature of what you're looking for. And sometimes when it gets perturbed in that way, data gets dragged out sideways from the main body of the data. So the point there is that looking for outliers is a subtle business in exploration. So a little bit about how our mind goes about the process of interpretation. And here's some quotes from Nate Silver's book. The numbers have no ways of speaking for themselves. We speak for them. We imbue them with meaning. I really love that quote. Assuming there's no quality control problems in the numbers, they're not the problem. The problem is the meaning we put on them, because we construe the meaning sometimes in self-serving ways that are detached from their objective reality. That's a fancy way for saying sometimes we stuff it up. And the other thing is, so the other problem, issue perhaps we have, is that the human brain is hardwired to detect patterns and respond to opportunities and threats without much hesitation. The human brain is actually a superb cluster analysis machine. It can see patterns in everything. And then the quote below there is just saying that sometimes that leads us to see patterns where there are none. But the point I like to think about here is that in our long forgotten history, if we're all sitting around in the savannah, looking at some grass, some long grass, those of us who saw the leopard first and got up and ran are probably our survivors, and hence this encouraged the design and the evolution of the extremely rapid processing machine, which is our brain. The other thing I'd like to say about that is those that sat around and formed a committee to determine whether the leopard was in the grass or not were hopefully eaten and haven't evolved, but I think that's materially untrue if you look at our current systems of government. Some more thoughts about what is data and what are patterns and what patterns are meaningful. Here's an example of coin flip experiments, 3 series of 200 coin flips. And if we call a head's a blue bar and a tail's a white bar, that's the pattern you get. It actually looks like a barcode. Now, interestingly, with something like that, if I asked you to sit down and write a random sequence of 0s and 1s, I can always guarantee that none of you would make up something like that because you actually think it contains a pattern, but it really is random data. Our brain tries to project a pattern onto it, tries to imbue it with meaning, to use Nate Silver's quote. Now I can go a bit further here. So if I take that random series of 1s and 0s, and if it's a 1 and I assigned it a random number between 1 and 50, and if it's a 0 or a tail, a random number between -1 and -50, and then just accumulate those numbers with time or from left to right, if you like, then I get that pattern below. Now, if I just regenerate the random patterns of 1s and 0s, I get a completely different pattern. And if I do it again, I'll get a different pattern again. Now, I think for the life of me, if I look at that plot, that sequence, the red plot underneath there, I actually can't conceive in my own brain that that's the result of a series of random events accumulating on top of each other. Our brain always wants to ascribe a cause and effect to it. Now, this is sort of interesting if you start to look at the way chartists work on the stock markets, how they try to predict, in this case, the gold price, and this is actually a while ago. But you look at those things there, and I think if you talk to enough people in history, they'll say trying to predict the gold price is a fool's game. I think they're probably true when you've got people looking at patterns like we saw before and ascribing all sorts of cause and effects to them. That's one example there, and that's just another example there. It's a completely chaotic system that's impossible to model properly. Just another thing here about looking at data in different ways. So that was the TSX pattern a little while ago, but just a thing to think about here when you're presenting data to people, and I'll just flick between them. So there's a line plot, for example. If you want to give the data that you're trying to show to someone some gravitas, then color it in underneath, right? Those things look completely different. Again, our brain can't help but imbue that data with more meaning because it's been colored in underneath. And what about correlation and causation? So these are some silly things, and those of you that are already into data analysis would have found some of these things on the net. But correlation does not imply causation, and just some things here. So a number of people who've died from becoming entangled in their bed sheets, I didn't actually know there was such a thing, versus the total revenue generated by skiing facilities in the US. Not only does it have a high correlation coefficient, so if you plotted a scatter plot, then you'd get a nice linear relationship, but even as a time series, the data overplots each other. But of course, there's absolutely no causative relationship between it. So correlation does not equal causation. The age of Miss America, murders by steam, hot vapors and hot objects. And just to get really silly now, US crude oil imports from Norway with drivers killed in collision with railway trains. So a lot of these things are just, I'm putting them in here just to get you thinking. So I guarantee by the time we get to the end of this hour, you'll never look at data the same way again. You'll always want to think it through. What's another thing? The way people present data. So this is really, this is sort of an example of flawed thinking in the first place and then coming to an erroneous conclusion. So what on earth is that? It's an example of survival deviation. So this is in World War II with the Allies looking at aeroplanes that are returned from Germany. And, you know, the engineers and the boffins are thinking, hey, let's have a look at the damage inflicted on the planes that came back. And where there's a lot of damage, we'll reinforce that to increase their survivorship. Well, the problem was that the sample is completely biased because the planes are looking at the ones that already survived. What they weren't looking at were the airplanes that didn't survive. And if you look at that and just change the logic around in your head, you think, well, there's no actual damage recorded on either the engines or the cockpit. And then, of course, there's a reason for that because they're the planes that actually didn't survive. So you could have, before they realized this, they would have been out looking at a whole program of engineering to reinforce these planes that were surviving anyway. This is another favorite topic of mine, something called Ascomb's quartet. I often tell people that if you're going to give me a table of parameters around data, fair enough, but always include with it some sort of a graphical summary. Now, the point here is that those series of x1, y1 through to x4, y4 all have the same mean, variance, correlation, and you could fit the same regression line through that data. But of course, they are completely different to each other and are illustrating different things. If you got given a table in a report without a graphical summary of it, you could be led right up the garden path about what that was trying to tell you. Right? And here's just another example, again, just a bit more humorous really, but the same means and standard deviations and correlation coefficients from the data at the top there versus something that looks like a dinosaur, a Tyrannosaurus Rex. So theme being always visualize the data. And that runs through to things like curve fitting. So just another example, the data underlying those red curves is actually the same. But again, this bias of the human brain wanting to impose its own pattern on the data. When you look at the red lines, you start to assume that the underlying data is actually different. You got to actually stare at a few of those plots for a while just to convince yourself that really the underlying data is the same. It's just the curve fitting that is changing. And I think curve fitting like this in data like that actually ascribes a fake gravitas, to borrow one of Trump's terminologies. That's really imbues the data with a fake gravitas. Now, just to get a bit more into the geoscience realm here. So here's an example where we've been out and we've collected say a line of soil samples. It could be analysis down a drill hole as well. We look at data like that. We plot it up as a line plot. Sometimes something was fashionable in the exploration industry a while back was to turn things into response ratios, which is not a bad idea. So rather than looking at the raw background values, looking at it as a times background. But at one point in time, it was fashionable to call background the median of the lowest quartile of the data. Why? I'm not quite sure. Maybe because to give you higher response ratios might be one reason. And you can actually look at that data and start to, again, imbue it with this meaning. And so just looking at that pattern, you might look there and go, there are some rabbit's ears, there's some sort of galvanic effect occurring in response to a massive sulfide deposit, which is sitting underneath there. There's a low there, and sometimes in superficial data, you get lows over faults that look just like that, actually. So you start to build up your interpretation, but in fact, that data is random data. I just used a random number generator to generate it that had a mean of 50 and a standard deviation of 10. And in fact, if you projected all of those data from the line across onto a histogram, it would give you a perfectly normal distribution. So again, like I said, this presentation is really just to get people thinking about data before the next time you look at it. While we're looking at line plots, here's some more fake gravitas, if you like, which can be applied to data. Other methods of curve fitting and putting confidence intervals on things. I put this there because one of my favorite gripes, really, when I see data people bring me data plotted up in something like Excel, is to apply a smoothed line fit through data like that. And again, it gives it a fake gravitas again. A lot of this data isn't potential field data. There's no reason to expect that there's a smooth relationship as you go along, but it just makes it look more real. And again, our human brain can't help but think that it's more real because it's got a nice curvy line fitted through it like that. So just beware when you're looking at data, looking at line plots which have been presented like that. What about fake news, for example, just to keep on this topic? So what happens in systems with noisy data and underdeveloped theory, like in the quote here out of Nate Silver's book is Earthquake Prediction and Parts of Economics, put in square brackets, insert some geoscience, is a two-step process. So the problem is that people mistake the noise for a signal, and then the noise creeps into journals, blogs, websites, and etc. And it actually sets back our ability to understand how the system works. Now, this has a few knock-on effects. So I just showed you that line plot before, which was generated from completely randomly distributed data. If someone showed you that line plot and said that that was absolutely slam dunk evidence that I can detect mineralization at 300 meters below the surface, I think you would have pause for thought if you were going to conclude that. It even has rabbit's ears, maybe. Just another example here. This is something called enzyme leach, which might still be around, was popular a while ago. But again, here's a buried mineralization as identified with the pink zone there, and a line of soil samples and a whole pile of chemical data measured on soils from a weak extraction. I think enzyme leach will give you something like 50 elements, maybe 60 elements in total. So there's a few things on a plot like this. There are actually more variables than sample stations, and the length and the lines of samples aren't very long. So I can pretty much guarantee to you if that sampling line was 10 times longer out either side of the thing you're trying to find, you would get repetitions of those patterns. So the whole thing is very much most likely noise and is actually not giving you a signal at all. But again, our human bias, and we want to imply that, look, we ran a test, we're looking for some mineralization, see if we can detect it through cover at the surface of soil samples. I collected this data and bang, I can see these patterns. The other thing to think about here is that if you've got not many sample stations and 60 elements and a narrow target, something will go up and down, or something will go up when you've got samples sitting above the mineralization. So just pause for thought. Design of experiments. So just another thought bubble here to think about. So false positives can dominate in an exploration program. So just by way of example, if you're planning a 5,000 sample program, assuming that 5 samples are located over a target, you can correctly identify those 95% of the time, you'd be pretty happy and you'd be pretty confident that if the target's there, you're going to find it. But the corollary of that logic is that if you can also correctly identify samples from background 95% of the time, you are still going to have 250 false positives to test. So before you embark on a sampling program, in exploration in particular, you need to think about some of these. You will always, especially not thinking too critically, if you go out and do the work and collect the data, you will generate what you think are anomalies which require following up. And if you've got bags and bags of false positives, you won't have the money to get through those to find potentially the 5 samples in amongst them, which are actually indicative of mineralization. It's actually a hellishly difficult task that we set ourselves. Exploration is hard, finding stuff is hard. It's best not to design programs to make the whole thing more difficult for us in the first place. So sample design, some comments around that. So there's a line of soils, if you like, a line of something. You've probably surmised already that I'm just plotting random data, and you would be correct. That is a line of data generated from a normal distribution. But what I've done underneath is sometimes if you're going out to run, especially an orientation survey, you have a target in the middle of the grid, and then you get told that we don't have enough money to analyze all of these samples. So start from wide space samples, and when you get in near the target, increase your sample density. You go, yeah, okay. So you go out and you collect that data. But the problem is, again, because your brain wants to imbue this with meaning, is that where you've got the closely spaced samples, you think you've got increased variance just because the samples are closer together. Those sample points on the plot on the bottom there all come from the same data that's plotted above it. But again, you look at it and you think something is happening in the middle where it is not, right? So just another thing to be aware of when you're looking at data. And to give you an example of this, where it's appeared in the literature, this is something Ryan Noble published, which is actually really good work. It does have the variance effect where you got lots of samples closer together, but Ryan et al. Weren't sucked in by that. They correctly surmised nothing much going on here. But the other reason I put this in is that, and this is a real problem for people like us and people doing exploration, is that 90% of all scientific publications publish positive results, right, which can give us a completely biased view of the veracity of some method that we might want to take out and apply. In a way, when you're not working as an academic, but if you're working in the industry and you're trying to find a method which is going to give you the highest degree of reliability in finding something, sometimes when you go to the literature, it's not going to help you, right? Because most of the important outcomes, which are actually negative results, something didn't work, never make it into the literature. But really, from our point of view, that would be far more valuable data. So there should be more of this, is the point that I'm making. That should be very helpful. Some other examples here. So here's some data that looks a bit ratty. There's some detection limit issues, things like that, by Ravi Anand, etc. But all of that's couched in language that says it's erratic, it's not really working, don't worry about it. Great. Again, really good to publish negative results. But then some other work, and this was actually some biogeochemistry, was actually showing some very clear signals in some of the elements. So there's good response ratios, good contrast with the anomalous values over background, and in a way, it's a way of amplifying the signal to noise ratio to make the signal that you're seeking more visible. So, you know, a nice piece of work. Other ways to amplify signals, and some of this stuff's pretty old-fashioned, doesn't get done much anymore. If you're collecting a soil or something else, stream sediment, lag samples, termite mounds, whatever it is, and exploration programs, often the signal that you're looking for is biased in a particular size fraction of that material. And it's very helpful to know what size fraction that it's concentrated in, because if you go and selectively take that size fraction, if you understand the process of how the anomaly was dispersed into the material in the first place, you can design a sampling program that will massively amplify that signal. And in this case here with gold, it just so happens that the gold here does report very disproportionately into the fine fraction. So if you were to go out and collect the fine fraction, you get a very, very unambiguous high signal to noise ratio anomaly, which is just fantastic. If you were to go out and collect the coarse fraction, which gets done in some parts of the world because people have misunderstood the process of anomaly formation in a particular district, you get nothing, right? You go out there and you see nothing. If you're wondering why in some exploration tenements, it's the 4th, 5th, 6th, 7th, 8th people that have owned that property that find something, a lot of it boils down to this sort of thing: poor design of experiment, poor sample design, poor selection of media, etc. And this is you can apply this process to many things about signal amplification. So let's take Chuquicamata, for example, copper mine in Chile. It's the largest open pit mine in the world, and it and a few deposits around it, and this is just a stat I found today, by 2005, God knows what the number is now, had produced $800 billion worth of copper. So you think something like Chuquicamata would be easy to find? Well, maybe not. Again, you've got to understand what's going on. So in the old literature, Chuquicamata was documented to have a surface expression of about 1 kilometre by 3 kilometres at around, say, 2,000 ppm copper. Now, of course, assuming you didn't know it was there, but if you're out running a stream sediment program to detect that, an immediate decision you need to make is what size catchment I'm going to sample with the best chance of detecting something like that. And that, frankly, is a whacking great anomaly. What I've done here is use that size of surface expression of a Chuquicamata and then assumed a background value of, say, andesitic rocks at 50 ppm copper, so everything the same, and everything being equal rates of erosion and dumping into the stream sediments. You would expect that anomaly to be progressively diluted as the size of the catchment increases relative to the size of the surface expression of Chuqui. Now, you don't need to do much. You don't need a very large catchment to start diluting the effect of seeing a Chuquicamata within it. And here I've just got a few things here. So if background's 50, if you've got a catchment that's just 5 square kilometres, 170 ppm copper rather than 50 is actually telling you may have a Chuqui in that area. If you get up to 10 square kilometres, you can expect an anomaly of only 110 ppm. So it's only twice background, right? That's sometimes not very compelling to the boss. And if you're going out running very large, if you're sampling really large catchments, a big screening program, and if the thing was quite a way upstream, the sobering thought there is you would not see it, right? No one's going to go and follow up a 62 ppm anomaly in a 50 ppm background. So again, these things are just food for thought. It's about understanding the processes that are going on in where you're looking at, and that way it's the process of forming stream sediments. Here's another one. So this is, we're over in Chile. Now we're here. I'm actually giving this talk from Perth in WA. This is out the back of Perth, if you like, the Cosmos nickel copper deposit. Again, people go out prospecting in these areas, not looking at stream sediments, in this case, looking at lags. And these are sectional views, not surface views. And this view on the left there is the nickel content of Cosmos. It was extremely rich nickel sulfide deposit. Now, at the top there, that's the surface. So if you're wandering along the surface, you really need to understand what processes are going on if you're going to correctly identify this anomaly as being potentially associated with the Cosmos. So you're out looking for massive nickel sulfide ore deposit. You look at the nickel data, there's nothing there. But maybe you expect the nickel not to be there because actually it gets more depleted in these horizons, in deep weathering horizons. But you know that nickel is associated with the copper. The copper hangs around more for all sorts of fundamental geochemical reasons, but the copper hangs on, especially in ferruginous materials in a sufficient environment. So you get a copper anomaly, which indicates a nickel ore deposit, but there is slumping and movement in the deep weathering profiles. So the copper anomaly gets bent over. So it's not actually lined up with the projection of the sulfide mineralization to surface. So if you know quite what you're doing, you might think there was no nickel. You might get your logic half right and say, I've got a copper anomaly, so it's associated with nickel. But if you don't get the dispersion angle correct, you go and drill in the wrong place and you actually miss the massive sulfide deposit. So process is all important. Here's another example of where understanding the process of what you're doing is really important to the interpretation of the data that you collect. Now we're out in the middle of New South Wales, and these are dry streams, but nevertheless, it does rain occasionally. Sheet wash and lag samples into the creeks, which are sampleable and actually make an excellent sample medium. In the middle of that, if you look closer, you'll see Allura. Allura is a large, massive lead zinc silver deposit, still being mined today. Now, if you went out, so before we looked at the example of trying to amplify the signal to noise ratio, and we're looking at gold in that way. So if you'd come into this district and thought, well, my fine fraction worked with gold also in an arid environment, but another part of Australia, I'm going to try it here in the middle of New South Wales looking for this base metal deposit. If you looked at that data and plotted it up, you'd say, no, there's nothing. You'd walk away. Again, why does the second, third, fourth exploration company find something and not the people previously? But actually, if you were thinking about superficial processes, regolith processes, and looking for massive sulfides, they would have formed a gossinous material, so a secondary enrichment with iron with a lot of trace metals in it that would derived from the sulfide minerals. Assuming these break the surface, I can expect those materials to be moved around by physical movement, physical disaggregation, not chemical disaggregation. Once you've formed a gossan, they're very resistant to further chemical modification. And so they get moved around as clastic particles, and they're also resistant to erosion. So the end result is that your anomaly ends up in the coarse fraction in the stream sediments, not the fine fraction. The last bit of knowledge you would have needed here to detect this is the iron contents of the stream sediments goes up and down, and the anomaly is only present in gossinous fragments, so it's related to the iron content. So you would need to do a correction for iron, in this case a multiple regression, looking at iron and manganese, in this case looking at lead residuals. And if you do that, then the Allura ore deposit stands out like the proverbial. So, just using analytics and mathematical methods to look at data without understanding process is dangerous. We can take this right through to lithogeochemistry, looking for alteration patterns, which again give us that three-dimensional information to vector us into an ore deposit. So here's an activity diagram. James will be all excited looking at this with an initial rock composition, an initial fluid composition, and a series of reactions that takes us from one through to the other. And so the reactions that occur here is a K-spark gets reacted to albite, albite gets reacted to muscovite, and muscovite gets reacted through to topaz. It's a sequence in an activity diagram, and it's a sequence in space, in geographic space, that takes us through to the mineralization. So how can we quantify where we are on the activity diagram in a very practical way? Well, here's a chemical space plot out of gas. This is one of the alteration diagrams in gas, the Davies and Whitehead plot, possibly the most useful alteration diagram in ioGAS. I would plot everything on that. But look, if you know what you're doing, it's just simply the sodium on aluminium molar ratio on one axis and the potassium on aluminium molar ratio on the other axis. You can put mineral nodes here and you can put tie lines between them. I can now actually overlay samples that represent alteration assemblages that are part of that alteration sequence you can see on the activity diagram. So here are the background rocks. So again, we put the blue dots and we see, oh, they make a sort of a pattern. But actually this is, you can infer from this is reaction 1, this is reaction 2, and this is reaction 3. And in fact, you could unbend those green arrows, and if you plotted them spatially, would give you a three-dimensional vector into the mineralization. That's not something you're going to learn with machine learning. That's something you're only going to learn by understanding the process that you're looking for and looking at it in a novel way on a plot and interpreting it correctly. A really important aspect of the sorts of data that we collect in geoscience, and sometimes this is lost on data science as well, is that all of our data, virtually all of our data, has a spatial connotation, spatial context. And so if we are looking at patterns and things in our data, if they don't hang together spatially, but they do in chemical space, then you've probably got to seriously wonder about whether you're looking at something that's important or not. Now there's an example there of trying to resolve out spatial patterns in data that has a high nugget effect. So if you've got pure nugget effect, so what does bad nugget effect mean practically? And this, by the way, is why you collect field duplicates. So if you collect field duplicates and they're not comparing very well if they're a metre apart, how can you expect to infer what's going on with samples that's 20 metres down and 20 metres away from that? You know, with data that looks like that, you can't really tell anything from it. A good way to induce a really high nugget in data like this is, like I said earlier, to mix up soil horizons, for example, a really high nugget, or use an analytical method with too high a detection limit. For example, looking at old gold data. So be careful, and you might have already predicted where this one's going. GAS makes these fantastic images, and if you see one, you know GAS has made it. But again, I'm just being my own devil's advocate here. So here's an image. It could be a gridded soil survey or some other sort of survey. It could even be geophysics. If you look at that, again, the brain leaps to these conclusions. You want to imbue it with meaning. You want to put your interpretation on that. And you start drawing lines on that. And man, oh man, in geoscience, once you put a line on a map, it's there for good. It's very hard to talk your brain out of the fact that it was never there in the first place, because as you might have expected, that is just gridded and imaged random data. You know, caveat emptor. And an example of that, or a practical example of that, so you've seen that and you've seen that. Now, if I come back, that's just an example of a gravity vertical gradiometry survey in Queensland, and X, or the little white circle there, marks the spot, apparently telling you absolutely unambiguously where Cannington is. Really? I don't think so. You would need many other lines of evidence to determine that. So that's one way of looking at a spatial component of data. Another way, which is 2D, another thing which is really important at looking at downhole data is looking at the spatial component in 1D. So that's how the data varies in its pattern and frequency downhole. And James will give you a good demonstration of this later on. But here we've adapted some work by June Hill from the CSIRO, and this is now in GAS and available. What it does is it applies a wavelet transformation to data. What you're seeing on the left there is a gamma log, and we apply the wavelet filter to the data. And to geologists, that doesn't make much sense. They go, what the hell is that? But when you go across, what June did was make a way of tessellating, or it's making a parquetry floor, if you like, to start to pick apart the different scales in the wavelets to identify geological boundaries, so to give us straight horizontal lines. So what does that mean? So here's an example. This is actually data plotted up in GAS. Again, it's a gamma plot on the left. You can see the wavelet transformation as the image underneath. You can see the tessellation as line work sitting on top of that. Now, when you draw a line up here, you're actually pushing geological boundaries across onto the gamma trace. It's up to you whether you want to be a splitter or a lumper, or you can pick a scale down on the extreme left and you get lots and lots of boundaries, or over on the extreme right and you get very few boundaries. There's an example there with the second coloured strip log where we've used a method, and James might go into it to help you to determine where to put the scale. Then you draw that red line up through the tessels and it picks out a series of geological boundaries for you. So here's the raw data. So there was the gamma data, there's the wavelet, there's the tessellation, there's the scale that was picked. And then we can automatically domain the data. And you see the solid line on the fourth line plot there is split into geological units based on those boundaries which are identified at that scale. And then we've gone further and actually grouped the geological units by the level of the gamma within those identified boundaries. So you can see you've got two purple units. Now, sometimes we call this quick log. So you can easily generate this if you have doesn't have to be geophysical data, it can be geochemical as well, but it certainly works well with geophysical data, something like total count gamma. And you can take this plot out to the drill core and you can take your eye straight to the important boundaries that are present. And it almost acts as a backstop. You might have missed something. So for geological logging and for cross-hole correlation, it's brilliant. And of course, the oil and gas guys have been doing this for decades. And just to illustrate that it's not completely black magic, if you like, here's a small interval from where the gamma where we've analysed with portal XRF. And you can see the total count gamma there is responding to potassium. Right? So the three elements that total current gamma respond to are potassium, uranium, and thorium. Obviously, potassium is interesting to us if we're looking for alteration, but the other two certainly help trying to differentiate between different intrusives, for example. So it's pretty basic data, but in a geological application, it's really, really useful. So we've been looking at a whole bunch of really univariate things, just different ways of visualizing things. ioGAS has many, many methods that James will show you a selection of later on. Multivariate methods, so unsupervised and exploratory multivariate methods. This one's just an illustration of what principal components analysis is doing to your data, for example. So there's three variables, three input variables. If you were to conduct a principal components on that, all it's doing is rotating that data cloud into the plane of the page, which would be principal component 1 or 2, which preserves the maximum amount of variance, or in geological terms, the maximum amount of information. That's all a principal components analysis is, but it is useful when we're looking at multi-dimensional, multivariable data sets. There's some enhancements in GAS as well to make it a bit more user-friendly and interpretable. What you're looking at there on the left is a biplot. And what we're doing here is we're plotting samples into the principal component space, but then also the input variables which have constructed that space. So samples, so that's 0, 0 in the middle. So samples plotting over here, for example, have high lead. Samples plotting over here have some combination of high copper, cobalt, etc. And down the bottom, gold, antimony, and arsenic. So that's sort of an aided multivariate interpretation, which can, you might see grouping. So from an exploratory point of view, you can see groups. The next question is what is causing the groups, and it really helps out. Then you can do some things that are really quite wacky in this sort of exploratory phase. And here what I'm doing is every sample on this has a coordinate in principal component space, and we're just representing that coordinate as a three-dimensional arrow in 3D. So these arrows are actually representing chemical contrast between the samples, probably illustrating 80 or 90% of the total variation in the data set. So there are weird and odd things you can do in ioGAS if you turn your mind to it. We have some other tools which are really quite useful in geoscience, but again, before you leap into these things, and James will show you, it's really important to do all of the simple things first and get your data organized. I must emphasize that. Here we're looking at a SOM, or a self-organizing map. It's a bit like principal components, but it's a non-linear way of trying to fit data into a simple two-dimensional visualization. Over on the right there's some geophysical data again, some mag, sus, induction, and gamma. It looks like a bit of a hodgepodge when you're just looking at the data plotted down like that, but you can apply a self-organizing map to that and then look at the classification of the self-organizing map and start to split this data out into three dominant geological groups, right? That sort of an analysis helps you with your logging and with your domaining. And another example of that here is here's a fence line of drill holes and a geological log underneath. They were logged with caliper, gamma, and mag sus. Quite ratty looking data, but again, thrown into a self-organizing map and then domaining the self-organizing map and then putting the domains back in a section view of the data. It's picking up some quite clear geological boundaries, which you can see here. And at this point, the mapping you can see at the bottom is treated as the source of truth, which is sort of not quite right because there's a big domain boundary running through here, evident in this data after applying the self-organizing map, which actually hasn't been logged. So again, it's an aid to the interpretation. And increasingly, we're seeing things in geoscience related to machine learning, so supervised methods. And these can have some quite novel uses, so not just looking at the data itself, but you'll see more of this cropping up in industry. So for example, reading sample numbers without someone typing them in, using machine learning, training machines, looking at just simple imagery or hyperspectral data to automatically interpret the presence of, in this case, white cerussite, just from simple photography of chips. Perhaps some of these methods, once they're trained, and the trick here is the training, can give you a much more reliable estimate of something like distribution of white mica than actually logging the materials themselves. The other thing I like to say about this is even if you don't trust it completely, it guides you. And even if it's 80% right, it can direct you to the places where you need to go and do your confirmatory observations. So just some finishing up remarks now about analytics, data science, and geoscience. I don't really differentiate between them now because I think geoscience has worked in data science and analytics ever since geoscience was conceived. So from that point of view, it's not IT. There's no standard operating environment for it, although obviously ioGAS can be of assistance with it. It's agile, dynamic, and scalable. The most important asset is the human, because it relies on an aptitude for the art of observation, mathematics, and logical reasoning. And I would add to that, you need to actually, it's no substitute for understanding the processes that you're looking for and understanding how those processes may be expressed in the data that you're looking at. Just to re-emphasize a couple of things, to come back to them, and again, because these are often missed by data scientists, is that the spatial aspect of geochemical data is crucial. And so here's a couple of univariate plots. There's a probability plot, there's a histogram. But if you go and make a map of that data, it actually maps the symbol for the old company IOGlobal, which was responsible for bringing ioGAS into the world. But again, just to make that link, there's univariate plots, there's a map. Always make some sort of a spatial representation of the data that you're looking at so that you don't get the wrong end of the stick, or in this case, the wrong end of the elephant, and infer and come to the wrong conclusion. So just at the end here, and I think this is really important from an exploration point of view, sometimes the most important signal you can identify in your work is a lack of one. The hardest thing to do in exploration is to walk away, and it is by far and away the hardest decision you're going to have to make. And to that point, do not be fooled by randomness. You cannot sit through this talk and end up being fooled by randomness. And my last slide there, which you can read, because we all operate under different pressures, which can encourage us to be fooled by randomness sometimes, but please not. So I'm going to finish up there. I just notice the sun's coming in now. Move around. I'm going to finish up there. Happy to take questions, or if people want to have a coffee, but I'll hand over to the organisers now.
Yeah. Thanks, Dave. Thanks very much for that. And I think that really sets the scene for why we start using ioGAS as a tool to help us with those aspects. I'm just going to reach out to Josh, Hugh, or Matt just to see whether there's any questions coming in from anyone that's either looking at this on Zoom or looking at this on the YouTube live stream.
Yeah, thanks for that talk, Dave. It was very interesting. We haven't really had any specific questions on your talk. I can just stress to the attendees, if you put any comments in on Zoom or YouTube, we are tracking the chat, and we will give them back to Dave and James to answer.
Oh, that's good.
All fine.
Excellent. But I think it does really set the scene. And, as I go through the next bit of this, and we start to look at ioGAS as a tool, I think, Dave, what you've been saying there is to have that in the back of your mind. And I know that when I use ioGAS as a tool, it's because I am exploring the data, because I'm trying to find process in the data that I know what I'm looking for. And I guess one of the things that I do a fair bit, coming back to your talk there, is when I'm looking at something like whole rock geochemical data, is that when I start to look at that data or analyze that data, I'm actually thinking really hard about what it is I'm trying to pull out of that data. And I think this is something we see a fair bit, is, you might look at that data differently if you're wanting to look for lithogeochemical clustering in the data, as opposed to maybe an alteration signal. It's either a cluster or a trend, as opposed to, say, you're wanting to look at some aspects of the geometallurgical makeup of the data you're looking at. And I think one of the things we see a fair bit is that, if you go and collect, and Dave, you talked about experimental design, right? And I think if we go and, as an industry, start collecting our data with a lot more forethought at stage one of any of our projects, that data then becomes very, very useful throughout the life cycle of that project, all the way through to, generating a mine and environmental reclamation. And, I guess one of my passions is starting to see people address how they go and collect geochemical, mineralogical, textual data up front, because its usefulness, you might not even fully understand what it might be used for 5 years down the track. But if you've done that experimental design well, suddenly that's a lot of value in the data.
Yes, we had a customer come to us when we used to be in the consulting business, wanting us to analyse 60,000 lithogeochemical samples for rock type and alteration vectoring, but they picked the wrong digest. They were all done by Aquaresia, which doesn't break down the silicate matrix of the rock. That was $1.2 million worth of assaying that was not very useful.
Yep. Fantastic. All right. I'll just give it a couple of minutes just to see if there's any more comments. I'm not seeing I presume, Matt, you're seeing the YouTube live stream comments.
Yeah, I'm monitoring the YouTube live stream. Do you want to take a 5-minute break, James, before we carry on into the next section?
Yeah, that would be good for me, certainly. So, it's just coming up to what, 2-3 minutes past now. So maybe we can kick off again at 10 past.
Okay.
I'll just disappear and fill up my mug with some coffee, and I'll be ready to talk by 10 past. And then if anyone's got any comments in the meantime, just chuck them in there. I'll be back in a couple of minutes and we can carry on the questioning.
Cool. Thanks, James.
All right. Back in a second.
That's all you gotta do. I'll hang around a bit, James, in case people are asking questions and things.
So Matt, you did send a couple of comments or questions. I think you sent them direct to me. If Matt is there, I'll just forward these on to Dave. Right here, Dave. Oh.
Dogs are getting ready for a walk. It's chaos.
Yep. Fair enough. So Dave, there was a couple of comments from the YouTube channel. I just put them in the chat there.
Yeah, just dragging them down. Use signal references. Signal.
So you want to maybe just
right.
Just shout out the question and then.
Yeah. So is it are we back on?
Yep.
So to speak.
I think so.
Very good. Everyone can hear us. All right. Hi, Dave. Many times geos use signal reference from other known deposits when interpreting data. How effective is this? Yeah, I would definitely try that. And there's in GAS, you can set up your own reference library of compositions, be them rocks, soils, or stream sediments. And we very much encourage people to overlay knowns on unknowns. You can learn a lot from that. And indeed, in that Whitehead alteration diagram I was showing you, if you're wondering where do typical rocks plot in that chemical space, you can go into the rock library and for example, turn on a calc-alkaline fractionation series of rocks, and you can see where it starts and when it finishes as it tracks across the diagram. If you're working in a calc-alkaline environment, it sort of gives you a reference line on that diagram where the rocks track when their primary composition changes due to fractionation. So deviations off that are some other process that's been put onto them. Another way to look at data like that, where you've got a signal, if you like, is with spider plots, good old-fashioned spider plots, and you can put in your own spider plot norm, which is it's not a multivariate plot, it's a stacked univariate summary, if a pattern, if you like. So if you make a norm of the signal and then put your samples on top of it, you can see how they deviate from that. I could talk to this for hours, I won't. If you've got a multi-dimensional data set, say if you've gone analysed 20 elements, and you've got a whole pile of data, if you've got reference rocks, append them to the end of the file and carry them through the analysis. And then if you do something like a principal components like I was looking at before, see where the reference samples project into the multivariate space along with your new samples or routine samples. There's quite a few ways of doing that. Could you please elaborate on the application of ion correction to the course fraction? Yes, so in those, so these are stream sediments, yes, but they're desert stream sediments. So you get, it rains, once in a blue moon, and you get all this coarse sheet wash going to the stream. So you get bits of quartz and bits of silicified sandstones and mudstones and things like that. But in amongst all of that is chunks of what you're looking for, which is the gossan with the lead in it. So if you just look at the raw lead numbers, they go up and down, but you don't know their significance unless you know how much iron is with it. So it's just a simple regression in the coarse fraction of lead against iron, and you did get a nice straight line, but that was background. But given a certain iron content, if the sample plotted above that had higher lead than you would expect, then bang, you had the anomaly. And in fact, that's even more extreme with arsenic, because arsenic's a really important indicator for all sorts of things, especially in deep latritized environments. But it sounds odd, but arsenic's actually everywhere, and it hyperaccumulates into very iron-rich terrains. And so again, you can actually hide an arsenic accumulation due to there being an arsenian pyrite, for example, in just background arsenic. If it just so happens that your sample might be 40 or 50% iron, might have 40 or 50 ppm arsenic, but the anomaly you're looking for might have 5 or 10% iron and 50 ppm arsenic. They're both 50, but if you take the iron into account, then you've got a much higher response in arsenic with that lower iron sample, because the only place that arsenic is in that material is in the ferruginous fraction. We're really talking about exploration geochemistry here, also, gas, but that's good. That's fine. That's the way to think about it. The known deposits. So I'm just.
So there was one more that came through.
Amplifying the signal or sample. How does he work with? In that case, you remove some portion of the sample. Yeah. So again, I'll come back to process, and it's a bit like the lead and the gold example. Is the signal you're looking for, where is it deported to in the material you're sampling or you're picking up? And that goes right through from biogeochemistry. So if using biogeochemistry, the leaf, the twig, the bark, the core of the tree, the north or south side of the tree, how old is the tree? Often, and this gets very philosophical now with exploration, often there might be a sample which is super duper identifying what you're looking for, but it's not evenly distributed across the survey area. So often you're better off going with the least, not the least, the next best option from a sampling point of view, if it's distributed everywhere, right? And so sometimes you see studies where people go and collect a sample medium and say, man, it works really well. And you go, well, shit, it's only on 5% of my exploration team. Well, what the hell use is that to me? It's useless. And this applies to soils as well. So sometimes we're saying, you've got to collect the beta horizon. We go, well, man, I don't know many geoscientists that are actually trained in soil science either. And I can guarantee you in any sort of a remotely complex terrain, even not that complex, I would challenge anyone probably on this call to go out and coherently and consistently collect the beta horizon soil sample. And that's why people, to get a repeatable sample, often go for a deep soil sample, like they ioGAS something, or they go just for A or A1, just at the very surface, because they're two samples you can typically get wherever you are on the grid. Is that it?
Yeah, I think that was the ones we'd received.
Yes,
I think that's all good. Yeah. Okay, well, that's good. Probably a good segue into your gas bag next week as well, Dave, which would be similar.
More random, actually, but yeah. But I will hang around a bit. So while people are chatting, if the organisers want to dump some of the questions in here, I can't really type back to them, can I, if they come up? But if it's pertinent, I might just interrupt and answer a question.
Yep.
Over a red wine.
That's all good. All good.
I am on Perth time, guys, remember.
Fantastic. Okay, well, what we might do at that point, and that's, so thanks very much, Dave. I think that, like I said, that's really set the scene, got us thinking about the data. And now we're going to sort of go through and introduce the tool and start to look at some of the ways we can use the tool to help us look at the data in the way Dave described. My intention, I think I've already probably blown the schedule out, sort of, but that's fine. We've just had a sort of a little bit of a break, so I might. My intention now is to just quickly go through and introduce ioGAS as a piece of software. Just a quick overview of the interface, where the different menus are, the kind of menu options that exist, the kind of tools that exist within the software. And then we can then start to go back and start to bring some data sets in and look at everything from kind of basic data import, data cleaning, plotting, and then start to go through the various tools, ending up, like I said, later on, we're looking at some of the more advanced analytical workflows that, again, Dave described, we might start to get into. Again, if you've got any questions or comments, reach out to the organisers here through whatever means, and we'll try and pick things up as we go. What I might do now is just go through for sort of half an hour on a basic overview before we have another maybe sort of 5 minute break or something to just get questions if needed. But reach out if you need to. Right, I'm just going to share my screen. Oh, right. So someone just needs to just going to ask one of the organisers to just stop Dave's screen sharing. Dave, can you just stop your screen sharing? Yep. Right, there you go. That's all good. And just going to share my second screen here. So you should be able to see my second screen, which is the ioGAS software here. Now, I'm using a version of ioGAS here, which will be released to everyone in, I think, well, I keep saying to Sophie 2 weeks, Dave, but a few weeks, 2 weeks. So this is coming imminently. Mostly it looks the same, but there's a few little differences that I might highlight as we go, because it gives you a bit of a preview to some of the new features that will be coming out in a couple of weeks' time. I think this is informally known as the COVID release. So what we're looking at here is the workspace of ioGAS. And we've got a set of menu items up here, a set of menu options down in here. And in essence, there's a sort of a left to right workflow built in some respects. So we start over here with file menu. And this is where we're going to do everything we can to bring data in, to maybe export data, to append data, to join files together. Anything you want to do around the data file and bringing data in is captured in this file menu. So very, very much sort of a Windows type flavor to the software. There's various ways to bring data in. You can either open a CSV, Excel file. One of the ways that I do quite regularly actually is to copy a section of data out of a table or something, and you can actually paste it in from the clipboard. That's quite useful to quickly look at data. There is also other ways of bringing data in. We do have some importers for portable XRF data, for instance, that do a few extra things to the data. We can bring data in from various sort of cloud-based web systems. ALS is WebTrieve for geochemical data. Our IMDEX Hub IQ system, which you can bring in portable XRF data if you're using our system, or survey tool data, IQ Logger for structural data. So various ways of bringing data into the system. And I guess more and more, we're probably seeing people use systems that actually pass data through APIs now, so secure APIs, more and more happening as we link all of our software systems together. And I'll talk a bit about that later. That's certainly something that's happening more and more in the industry. There's also abilities to add data in. So if you've got a data file in and you want to append new data to that file, or you want to join data to that file as well, there is methods for doing that. So, appending data, obviously you've got new data you've collected that day, you want to append it in and keep analyzing it. Joining is really useful if you want to bring in extra data against, say, a common sample ID. It could be that you've got portable XRF data and you want to bring in sample metadata with a GPS coordinate. You can then join those data files together on that common key and analyze it like that. And then once you've been doing things to the data, there are ways of exporting the data as well, again, back out in various formats. So one of the ways that ioGAS works, I guess, is we bring the data in, and then that data sits within ioGAS, and then we can save it as a .gas file. So what that really means is you bring the data in and you work from a .gas file. You're not touching that raw data. So as you manipulate the data, change it or whatever, you're never touching the raw data again. You can bring extra data in. But that gas file is obviously really useful because it can be shared amongst your co-workers and that kind of stuff. So that's the file menu there. Once you've brought data in, and I'm just going to bring in some, I've probably got some data. I've got some data already loaded here, and you can see up in the top here what version I'm using and what data set is loaded at the moment, and even what elements I've got selected right now. This is actually a demo data file here. So we've got data loaded, so we can see as we go to the next screen that all of our menu options are available to us because we've got data loaded. So as I said, there's a kind of a general left to right workflow here. So the home screen is really where most of our common menu options exist. So places where we can quickly plot, look at some of the key plots here, map plots, some of the things we want to do with the data to select variables in and out, to attribute my data, and I'll talk a bit about that in a second. As we go right, we go into a data menu, which is where we want to do things with our data that maybe needs a bit of cleanup. Maybe our data needs cleaning. Maybe we have a massive data set and we want to take a subsample of data to work with. That's something we can use a lot. So those kind of options are sitting in here. We may want to take out spurious data rows or columns, things that aren't being used, blanks, just generally clean it up. And I'll go into the details on most of these in a bit. The calculations menu is where a lot of our inbuilt calculations are sitting. So when we bring our data in, we can alias the data, and I'll show you that process in a second. We can alias the data and tell the software what of our columns are related to what chemical elements. And once it knows those internal relationships, this is really key to the way ioGAS works, it then allows us to then do a lot of operations very quickly. So we can then calculate new columns of data. So these provided calculations here, and I guess, David, I think I'm right in saying this, we're always open to hear people's ideas on new things that should be in these menus. We're very responsive to that. And I think even in this version, there's some new calculations and new diagrams that have appeared.
Yeah, every email we get gets read and stored and goes into the tracking list. Yeah.
Yep. Some of these built-in calculations, I mean, certainly when I've shown these to certainly some of the PhD students I've worked alongside, they've almost been in tears when they've realized how easy it would be to suddenly plot a molar plot or something like that, as opposed to trying to reformat the data in Excel. So you can see things like hydrothermal alteration indices. So we can quickly calculate some of those indices and calculate them and plot them as a new column within the software. Normative mineralogy, if you've got the right data, this probably doesn't have some of the data existing in it, so it's grayed out. But we can have normative mineralogy here. Molar ratios, so these are the kind of common molar ratios that people take a while to calculate otherwise. There are other things, inbuilt exploration indices, the iron conversions, petrogenetic ratios. And then down in here, we have ways of transforming our data. So, not all of our data is normally distributed, and some of our routines require normally distributed data. So we have ways of doing all those transforms. So we can quickly generate a log transform, a center log transform. So those kind of things, molar functions. And then we've even got the ability to calculate your own set of calculations. So you can put in here what you want to use, and then you can actually start to calculate your own custom calculation and save that at the end. So there's a lot of flexibility here to set this up to calculate what you want. One of the nice things that you'll find in ioGAS is that where there are things like the ability to do a custom calculation, the ability to do a custom diagram, those aspects can all be saved. And they can be shared amongst your co-workers. So in a project, you might be working, a few of you using ioGAS, and someone comes up with a new diagram, someone comes up with a new calculation. You can actually share that amongst your co-workers. So that's the calculations. Analysis is where the real fun starts. And again, I tend to think of this as it goes from the more routine stuff on the left to the more exciting and potentially really hairy stuff on the right-hand side. I don't know whether that was intentional, Dave, but yeah, it sort of starts to get really exciting when you come into here. So we can see here, this is where we're going to do stuff with the data. So everything from just looking at the summary statistics. So I've got a few elements selected here in my data set. Look at the summary statistics. So I've got those kind of standard summary statistics here by color group here in this case. So things you might use in a report all the way through to doing transform calculations, outlier analysis, different ways we can do that. And Dave talked about how we might want to look at outlier analysis in his talk earlier. The supervised learning methods, these are in essence machine learning methods, if you like, or analytics routines that take a predefined classification and allows you to build a routine from a training data set that you can then apply to new data. Or the unsupervised learning methods, which is where we're going to let the data speak for itself. We're going to let the data tell us how it wants to cluster or how it wants to fall out in trends. And so we've got a whole range of things sitting in here. For any of these menu items, you can, if there's a down arrow, it means there are more options sitting underneath it. You can click that. In most places, there are tooltips available in the system here. So we'll look a bit of this, and we'll play with some of these tools a bit later on today. The graph menu is a whole range of different standard graphing types for plotting your data. And again, if you think about trying to do some of these in something like Excel, you'll know the pain of trying to do that. And now you've got it at a single click of a button type aspect. So if we want to look at something like a scatter blocks, for instance, and this is looking at zinc versus nickel here. I've got my XY scatter graph, and I've got my, these are my different color groupings here of my data. I can see the two key plots for that data as well. So immediately you've plotted a summary visualization of that data, as Dave was describing. You've got that in a single plot of a single button click. You've got a summary of that data. Again, really useful, and you can then copy that as a bitmap or export it to suck into a report. All of these labels and stuff can be configured to look nice as well. So you can easily interface from ioGAS back into your reporting software or put it into a PowerPoint, something like that. Anytime you've got a window up, there's a set of icons that exist on the right-hand side here that are option icons that work on that window as well. So you can see a whole range of different options here. And again, we'll go through some of those in a minute. So any window that's highlighted, the options or optional icons will exist on this side. And not that I've played around with it too much, there are ways of configuring your window should you prefer your options to sit on the left-hand side or the right-hand side. You can configure the whole GAS workspace to look and feel in the way you want. We don't do dark mode yet, but I have seen that request come through a lot of times as well. So we'll just shut that and we will come back to these. The map obviously is dealing with your spatial data. So now we're going to look at spatial data. Here, I'll just quickly plot up the variable map. So that's just the quickest plot here. This data has a spatial context in a map sense. So we can see quickly, what our elements are doing, and just plotted on a map like that. And there's various ways of looking at that. If you've got three-dimensional data which contains an XYZ coordinate, then we've got the ability to plot that as well. So again, trying to link in that spatial context for your data. So go and look at your data in your graphs, in your analytics, then bring it back to the spatial and go backwards and forwards between those two aspects as well to really understand what your data is telling you. And you start to see that we've actually got ways of linking back through and exporting this data through to other software packages, MapInfo, Google Earth exports. We can grid, we can do things like RGB gridding and that kind of stuff. So there are lots of ways of plotting the map data and then taking it through to other third-party software like Google Earth, MapInfo, QGIS, if you want to work with it in your own GIS. Structure, I've got a whole section later that I want to just show you and demonstrate the structural analysis menu was probably something that's come in relatively recently. You know, I guess as a company, we realized we were, with our core orientation tools, we were probably orientating, you know, 70–80% of the world's diamond core. We built the IQ logger device, which was a digital structural logging device to give to geologists to start digitally structural logging their core. So it seemed only fit that we then round that solution out by putting some structural analysis functions into ioGAS as well to allow people to do this. And I think we've had a whole range of names involved in vetting and helping us feedback and test this. The likes of Nick Oliver, Brett Davis, Rod Holcomb have all had plenty to say about what we put in, what tools we put in here. So, you know, I think this is a foray now of ioGAS away from just the pure world of geochemistry to now having some really useful tools, taking advantage of the way the interface works for structural geology as well. And I've got a whole section later to show you how that can become useful. And the diagram menu is where we have our pre-built diagrams. So this is just a wealth of possibilities in here. And, you know, if there was one place you'd want to bring your geochemical data, mineralogical data, if you've got processed mineralogical data, we've got some of those diagrams in, you can come into here and look at some of those pre-canned diagrams. Dave talked about Davis and Whitehead earlier as an example of a kind of diagram where you can just quickly plonk your data on there and have a look at what it means. And I'll show you a bit of that with some data, some lithological data I've got later. But you can see here there's a whole range of diagrams that exist in here. And for any of these, they will be black. If you've got the right data to plot on here, it will do the calculations for you. It will work out the axes for you. It will put your data into the diagram. And for any of these diagrams, the references and all of the information you need for those diagrams exists in the tooltips as well. So really a lot of information here. And again, as Dave talked about later, if you start using ioGAS and you say, we should really have this particular diagram built in, let us know. It's easy enough for us to put in. But also, there's a way of you building your own diagrams. So we build an interface there to allow you to construct your own custom diagrams. Again, really useful for people working in mine sites, for instance, where they're doing a lot of geometallurgical testing, and they might want to build classification diagrams that help them to classify the kind of way that they're classifying their ore, the way it might process, that kind of stuff. We've got lots of people doing that. And again, if you build your own diagram for your project, you can then share that amongst other people. And then spider diagrams will be the menu, the last menu here. Again, a whole series of pre-built spider diagrams, so you can normalize your data to really whatever you want. And of course, because the development team are a little bit crazy, there is a special interest group, and there is the other group here. So you can really start normalizing your data to a whole range of things. So if you really want to report your soil geochemical data normalized to the human body in your next ASX release, we do allow you to do that. So nothing is out of bounds here. And again, you can build your own custom spider diagrams as well as custom normalization parameters as well. So all of that's possible. And I guess right at the very end here, and it's worth pointing this out, there's a really comprehensive help menu included in the software. You know, I've probably learned ioGAS. I presume you can see that. I probably learned ioGAS myself, mostly from looking at the help menu to start with, and in many respects, I've probably learned a bit about statistics from reading some of the detailed information included in this help manual.
Yeah, indeed, it's not a software help file, really.
Yeah,
it's not a bad lesson in geoscience data interpretation with actual worked examples, actually.
Yep. Yeah. I mean, I refer to it all the time. There's lots of times when I forget exactly the details behind a method or exactly how I'm supposed to use something. I just jump in here. So very, very comprehensive help. A lot of work has gone into this, it has to be said. So again, you can flick through here by menu item, how to do anything you want to do. So it is certainly what you'll find with ioGAS is it's a piece of software that you have enough information given to you to really jump in with both feet, a little bit of a starter, and you'll be off and running. The other thing it's probably worth pointing out is that we have a really proactive support system around ioGAS as well. There's some really good people that support ioGAS. And there are ways of you can use our customer service portal or email support. If you've got a problem, jump on, put a request in, someone will get back to you. And so it's well supported as well. And there is a set of training videos, and I think there is plans this year to enhance that. And I've got my own plans to do some workflow videos as well. And I think that's one of the things we'll try and work on a bit in the next year is more of the workflow videos where you're going from start to finish on taking some data all the way through the various steps, because I think that's where people are starting to get real value in using a tool like ioGAS. So that's a general overview of ioGAS, of really what the interface looks like, the workspace. I now want to just probably at that point, let me just check on the time. So I'm just going to jump in. I'm just going to start running through some of that stuff. We're going to start off pretty basic, some of the more basic functions, and we're going to extend what we do as we go. And I've made various notes, and what Dave was saying as well, of various things that I should probably try and demo. And I've been trying to be very organized here. I've got data sets lined up. I've got a run sheet here. I've got a set of notes, and I can almost guarantee within about an hour, I'll be completely off-piste and I'll have gone somewhere completely different with it. But that's fine. This is all good. This is the point of the software. So just going to go back and what I'm going to do is I'm going to show you, what it might be like to bring in a data set that you might have available to you. So I'm just going to say no to that. And I'm going to bring in this data set here, which is sitting as an Excel file of a set of geochemical data, but it's not entirely clean data. So it does need a little bit of cleanup when we bring it in. This is really typical of historic data in particular, when you bring in historic data. And some historic data that I've been involved in bringing into ioGAS is a hodgepodge of a whole range of different things. And actually, a big chunk of your time is actually cleaning it up and understanding what it is you're looking at. So I'm just going to open that file, and it brings the data in, it imports it. And the first thing it's going to say is that it's found a column here with a certain heading that has no data in it. So I'm going to flag that for deletion. There's no point in having an empty column in my data file. So yes, that's fine. And then what we're going to do is all of our data files open up into this column properties dialog. And this is where it allows us to allocate or assign the data to, so geochemical data, we assign it to the actual alias for that geochemical element. Plus also allows us to allocate spatial information as well. So for this particular one, so sometimes ioGAS will do a pretty good job of guessing what columns relate to what. And you can see here whether it's numeric or textual columns. We can see here that we've got geochemical data that has mostly numeric, but some nulls. That immediately tells us we've probably got some data that needs cleaning up. And what we can do here is we can actually allocate our eastings and northings. We've got eastings, we've got northings here, and we've got the longitudes, I think, set here. Where are we? Longitude, latitude, and the grid type. And by setting all of those up front, it means that, we've got a unique ID as well. There you go. By setting all of those up front, it means when we come and do our map conversions, we want to export data from our maps and that kind of stuff. It knows the spatial location of those. So to pull a diagram into Google Maps or something like that, it knows exactly where to put that data. Now, the other thing we need to do is we need to what we call alias the geochemical elements. And for this particular data file, we've actually got a whole hodgepodge of stuff in here. Now, ideally, So this is a good example of bringing in a data file. You don't entirely know what you're ending up with. Here we can see that we've got, for instance, we've got for iron, we've got 2 columns of data for iron from 2 different methods. And we want to be able to, well, we can either combine those into one column, and we can do that outside and then bring it in, or we may want to choose one of those methods over another. But what we want to do is we want to tell ioGAS which one we want to use as iron and which one it's going to treat as iron and what unit it's going to use. So if we hit the guess alias button here, you can see what it does is it goes through and it makes an informed guess about which ones of those we want to use based on anything it can find in the column header to tell it about the units being used. So here, percent shows us I'm using iron percent and the element oxide here. So here it's aliased iron, ICP-MS percent data as iron percent, and it's kept the iron AA data there as numeric. So we're using iron here like this, and that's your choice in cleaning this up. So this is quite a dirty data set really, but I wanted to show you some of the data that's really typical when you're bringing in historic data in particular. I'm not going to do a full cleanup on this. So what you can see is when it aliases a column against the element, that goes green. And then we know that that column is being used for our beryllium or for our barium, and our barium's coming in that unit. By knowing the unit, of course, it means that when we go and plot diagrams later, it doesn't matter what units those diagrams are needing to use. It will do the calculations internally itself, no problem. So we can just go through
and the element oxide conversion, James.
Yeah, right. Yep. So if you, which is a good one. So if you want a SiO2 over TiO2, you're not having to worry about that because you've aliased the element. It knows all the internal conversions needed. It will just do that automatically when you plot that diagram. So I can try and show you some of that stuff. So we've gone through, we've selected some stuff there. Like I said, it's a relatively dirty data set. You can see that one column there that was all blank has been marked for deletion. So that will strip that out when we import this. So we can go OK now, and it will take that column out. Yes, and it's now brought that data in. So you can see a few things that happen here. So if we go now to the home screen, and we go to the select variables. So really what you're seeing on the screen there are the 2 kind of windows you will use most is the select variables, i.e. what am I playing with at this precise moment in time, and the attribute manager. And the attribute manager is how we will attribute our data. And we have ways of either filtering it, attributing by size, shape, or color here. And I'll show you some of that stuff in a bit. So we've gone through, we've brought that data in, we've aliased that data. Now I'm just going to bring in so actually I've already spotted one mistake there that I didn't pick up. So actually the rhenium there, I don't think we have that in this data. But if I go back, if I want to set the alias to something else, I want to change the definition of one of the columns, I just go back to column properties. And you can see here, it's accidentally looked at rep stat and thought that was rhenium ppm when it's not. So we're just going to reset that back to what it is originally and bring that back in. So yes, you can always go back in and set that as something else. So we know that this data probably needs a bit of cleanup. So what I'm going to do in the first instance is I'm just going to bring in all of those that we alias. So all of those green elements there, I'm just going to bring those in one hit, and I can do that just simply with this select all aliased green arrow, and that will bring all of those green elements across. If I want to take everything away, I unselect all. If I want to bring everything across, it's this arrow here, or I can multi-select a set of components and bring those across by themselves, bring all the numerics and not the aliased, and bring all the text across. So there are ways of selecting and unselecting your data. So I'm going to bring those across. If I want to change the order that my elements are stored in here, because for certain things like plotting an XY plot, for instance, you may want something on the X and everything else on the Y. I'll just change the order here with these arrows here, so we can just move aluminium up to the top there. And I hit OK. So that's got those all selected. And if I just, this may or may not work, there's quite a lot of elements selected there. If I just want to plot those as a simple XY plot, I could just hit that button. It's going to go away. Quite what this will look like on your screens, it's all a mystery to me. See, already I've gone off piste. And so then immediately you can see all of those elements we've selected plotted against aluminium in this case. So it all looks a bit small there, but we can see that grid of diagrams there. We can immediately see that certain elements like tantalum there are all below detection limit by looks of it. So we can immediately see also that we've got some that have some data and some below detection limit data. If I want to look at any one of these plots a bit bigger I'm looking at a plot like this, I want to see them a bit bigger, I can right click on that plot and then bring out the XY plot by itself. And there we can see that plot by itself. So we can see the aluminium versus calcium in percent there. So that's a quick way. We can see all the data coming in, but we know it needs a bit of cleanup. So if we go to the data menu, one of the places you might spend some time if you've got old data or data with a little bit of cleanup required is the data doctor. Data doctor and missing analysis is probably your two greatest friends when you're bringing in old data that you want to clean up and start using. So a couple of things here. I think probably I'll just start with the missings analysis. This is really useful. And this is particularly if you're dealing with a data set that is an amalgamation of a whole set of a whole history of data analysis that's been done or different programs. So if I've got those green elements selected, I hit missings analysis. And what this now shows me is a plot that shows me how many rows have which of my elements present. So we can see, if we look down to the bottom here, that I've actually got 1,869 of my rows have all of those elements present within the row. So there's 1,869 analyses that have everything present, all of those elements present. But you can see here I've got 2 rows that have that are missing 7 elements. I've got 970 rows that are missing 17 elements. And if you look across, you can either look in here or you can look across. You can see which of those elements are missing. And all of this stuff, when you do this, there's a couple of ways of using this data. So you can attribute your data by these different groups. So what that allows us to do is we can say, actually, we're going to now filter out everything that is missing other elements, and we're just going to deal with this 1,869. So what I can do there is I can attribute this to the filter. I can click apply, and if I go now to my attribute manager and I look in my filter, it's now got groupings here based on what is available and what isn't. And what I might want to do is I might want to turn off everything except only those rows that have every element present. And now I'm filtering everything else out. So at this point, because I'm using the filter, the data is not removed. But when you use the filter, the data is kind of held outside of the data set. So if you're doing a statistical analysis, if you're doing anything on that data, it is doing it only on that data there that we have showing. So it's a really useful way of quickly going through dirty data or data with mistakes in it and cleaning that up. The other thing we can do here, now we're just looking at the data that has a full suite of elements in it, is we can hit Data Doctor, and I'll just pull it over to the right screen. And Data Doctor now goes through and it informs us of some of those issues that it's found in the data set that we probably going to cause us problems, right? And the classic one here, and you can see it, is that we have got a set of negative numbers, and they will probably be related to below detection limit in whatever method was used in the lab to report those numbers. So you can see here, it quickly goes through and it goes, here's a set of negative numbers here. And it's going to give us a choice of what we want to do. So we can ignore that. We can just bring the data in with negatives. We can just attribute all of those data points to a color group or something and deal with them separately. Or one of the options we have here is to replace those negative numbers with something. Now we can go through and we can choose to replace it with a null, or we can choose to replace that with a number here. And what it's using here is the number is its estimate of the half value of the lowest or the estimated detection limit in the data set. So it's gone through the data set. It says I've got valid numbers down to about this level, which is probably about the detection limit, and this is giving us half that estimated detection limit. So this is just a way of allowing us to replace a negative or a below detection limit with a number that's valid, but that is representative of something that didn't report above detection. So we can go through and we can click replace all, and we can apply that. Now, one of the really useful things here is we run a log of what is happening to our data set. So again, if you're storing this, you're saving this GAS file as you go and you want to share it with someone, we're actually storing that log, and so people can see exactly what has happened as we've gone through and cleaned up our data. And all of that stuff you can copy. Any of these windows can be copied and also pasted into an ongoing report. So if your job is there to do the QA/QC of a set of historic data you're bringing in on a project you've just acquired or something, you can actually copy and report all of these different processes out and have a record then of what you've done to that data. It's all auditable. Right, so we've just done that. We've taken that data, we've cleaned it up, we've stripped it down to the bare minimum. We've got a set of elements selected there. Now, what I'm going to do now is probably for this data here, I'm going to not choose as many. What I'm going to do is one of the other things we have in the select variables is the ability to select a set of variables based on common usage. So up here in the provided group, you can actually select all the majors, the immobiles. You can actually select pathfinder elements that are typically associated with certain deposit types. So you can see as you go down through this list, the kind of things that you have, the chalk files, lithophiles. So you can quickly select those. So I'm just going to go and select the majors in this instance. So it selects those, it selects out of that list, it's selecting what we have available to us. I'm going to click OK. And one of the things I'm going to do in the first instance, I'm going to go back to the home screen because it's a well-used method, is I am actually going to click the SPLOM tool. And this is probably one of the things that typically I would use whenever I'm looking at a data set and I pare it down and I want to just get a quick assessment on the quality of the data. I want to get a quick assessment on anything, any structure in the data that I'm seeing. I'll use this thing called a SPLOM. It's a, what does it stand for, Dave? Mine's gone blank. Scatter plot.
Scatter plot matrix.
Yep, scatter plot matrix.
Yep.
If you've got a big data set, actually, I have seen people produce a SPLOM and then plot them out on some A0 plotter, if you've got one available in your exploration office or something, and then they sit there and stare at it like that. But these days, actually, we have some pretty big monitors and pretty good graphics cards, so you can cope with some pretty high resolution stuff. What this is, what's that?
A0 plotter, is that what you call it?
An A0 plotter, yeah.
Right.
Yeah, on those big plotters.
Yeah.
I've seen that happen in a certain mine office. Yes. When Nick Oliver was present, I believe. So this, the scatter plot matrix, what it's doing here is it's plotting every element against every element in a matrix, and then it is plotting the probability plot of those elements down the middle here as well. So here we've got the magnesium column. We can see the magnesium distribution here. So this is normal score versus the concentration. This is the distribution on a probability plot. And what that's really useful for doing is to show you whether that data is log normally distributed or normally distributed. And so we can see here, we can look at here, when the data is looking like this, it's probably got a more of a log normal distribution. So we've got a bit of a mix here. Potassium's kind of starting to become a bit normal. And then we can see the various things plotted against all the elements, plotted against all the elements. And it's really useful to just see what you're quickly seeing. So when you look at something like this, I go, well, magnesium and calcium, there's a strong correlation there, that data, with some data sitting off that trend. I might want to look at that in a bit of a closer detail. I can quickly go, right, yep, I can see what's going on there. So it's a really useful way of looking at the structure in your data set when you first brought it in, to give you an idea of what's going on. And you know, you're the ones that know your data the best. And so, as Dave said, always think about where that data comes from, the processes you're looking at. But this is quite a nice way of then looking at that data, just very simply to say, am I seeing structure? Am I seeing groupings, clusterings, trends? Is there elements that are really correlating strongly in some way? And so this is the visualization part of starting to explore that data.
Yeah, and that's a dolomite control line.
Yep. And then something moving off that control line that might be important.
Yeah, plagioclase or calcite or both or something.
Yeah. So you know, immediately we've been able to kind of bring in a complex historic data set that's been a bit dirty. We've gone through, we've cleaned it, we've plotted this up, and we've gone through, and immediately we can see something that has a process control that we believe that might be really important. And actually, well, because you've said it now, Dave, I'm going to have to do it. So this is it. This is me going off piste straight away. The run sheet has been left to one side. So Dave talked about the fact that this looks like a dolomite control line. Right? We've got magnesium, we've got calcium, some kind of carbonate control line causing the relationship to occur. So we can test that. And one of the ways we might test that is if I highlight this plot here. It's just a simple XY plot. And we look over on the right here. One of the things we have here is an option to show mineral and rock nodes. And so Dave talked about this. We actually have the ability to plot the end member composition of minerals and the end member composition of rocks onto these graphs, because we've told ioGAS that this is calcium and this is magnesium. It knows where to put those.
This is why it's so important to alias the input variables so GAS can do things like this for you.
Yeah. So quite an overwhelming list. So I'm just going to clear all the minerals here. But you can see here, if we look at the carbonate list here, and you can see here dolomite, and I'm just going to select that on. Oops. Oh. Okay, and sorry, just a bit of lag on that because I've actually got the big plot showing, I think. And I'm going to put calcite on there. We know where that would be on that plot, just along the line, but I'll put the dolomite line on anyway. But anyway, you can see the range of minerals that you could choose to plot here. So I've selected dolomite there. I'll just close that, and I'm going to turn on the rock node, and I'm going to click it. So on any of these icons, clicking them multiple times runs through a set of options. If you don't know where you are in the option list, you can right click on the icon here, and it gives you the different options. So I'm going to put the node line on, and what you can see here is it's put a line onto this graph, and this is the line of the magnesium calcium ratio related to end member dolomite. And so immediately we had a hypothesis then that this was a dolomite control line that we were seeing, and straight away we can see we put that line on, and we can see that it is absolutely, that trend is sitting absolutely smack bang on that dolomite line. Of course, the actual composition of dolomite sits off here because it's an end member, so we can actually zoom out and we can find where the dolomite is. Oh, here you go. So here you go. Here's the dolomite. And so here we can actually say that, we can start to make assumptions here about the fact that these samples up here, they're pretty well dominated by dolomite. And the samples down in here are obviously some mixture of some other component plus dolomite.
See, this is where a pure data scientist is not going to tell you that they're going to tell you there's a regression, but there are these weird things plotting up to the top left and nothing underneath the line. They're not going to have any idea what the causation is of that. And this is where like I said, geoscientists are data scientists, and we are involved in analytics. So that's a mixture of visualization and process knowledge.
Yep. So, I mean, it's a great example. And actually, I didn't pre-can this at all. Actually, this is not one of my data sets. So that was very nice that fell out. And honestly, this is a really good example of what happens with ioGAS consistently, is that when you start to bring this data in and you visualize it and you ask process-related questions like this and you use the tools available, you start to find things out about your data that would be really hard to see quickly otherwise. Yeah, so here we can see this, even on this graph, we can see that there's data spreading up to the left here that is potentially heading towards the calcite end member. So there could be some combination of effects here where we're getting a dolomite control and then calcification of that dolomite with the data drifting off up to the end member calcite there. So it's a really nice example. Again, if you were doing this, you can then copy, you can get this plot looking really nicely. You can copy this and you can then plonk it into a report. Now, when you're looking at something like this, one of the things you might want to do at this point is you might say, well, okay, that's really nice, but what does it mean for these samples that are sitting up towards the calcite end member? What else do those, where do those samples plot in those other data plots? How can I kind of keep those samples to one side as being samples that might be of interest to me? So there's a couple of ways. So this is one of the new tools that's coming. So you can see here, I'm hoping my computer's going to cope with this, depending on my graphics card. So one of the new tools that I think is coming, I don't know what do you call this tool, Dave? Is this a highlight tool? Is what I've been calling it.
Flash selector.
Flash selector. There you go.
Not in as it's flash.
That's.
But it is flash. But it's a flash selector.
Sort of Flash Gordon theme tune playing in my head right now. So the flash selector. So I want to say, well, okay, I've got these data points up in here that might be of interest. I've got everything else plotted in the background here. Where do these sit on these graphs? So there's two ways to do that. We can either color these using our attribute manager, or we can use this very quick method, which is the flash selector. So if I hit the flash selector here, which activates it, I can then draw a polygon around these data points, and I'm going to make an arbitrary selection here of data points that's sitting above the line. And I've selected those, I've highlighted them there, and immediately you can see in the graphs underneath, I'll just shut that for a second. Immediately you can see in the graphs underneath where those highlighted data points exist on those plots as well. So we can look at where those data points are sitting on other plots. So if we look at something like calcium phosphorus, we can open that up. We can see that at least some of those are sitting with elevated phos as well. Kind of makes sense if we're getting calcification. So we can immediately see where those are sitting, and we can see where they're trending to. So we can look at, here you go, manganese, calcium. We can see the dominant, those are all sitting up in here. The highest calcium ones are clearly, they're the ones we highlighted. But it's quite an easy way to then see where those data points are plotting. So I'm just looking now. I am doing this on the fly, but it's always a good way of doing it. So if we look at something like, so calcium, sorry, potassium. So it's a good example actually of one of the data problems we have with certain laboratory methods. So the potassium here, we're seeing it form in very discrete channels here. What this is that the method that was used here, some kind of ICP method, but whatever method was used here, actually we're down at a level here where it's starting to bin the data. So we're down towards detection limit for potassium here, and it's starting to bin the data. But it gives us an idea here that a lot of our highlighted data, so again, elevated calcium, but they're actually plotting in the lower end of the potassium. So we're not seeing high potassium. Anyway, that just gives you an idea of, oh, there you go. There's at least some of our data. Oh, that's the FOSS again. Yep. So it gives you an idea of how you can quickly move around and say, where are our data points plotting? What does it look like? What else is plotting in the same way? I'm just going to shut that just because now I've still got those data highlighted, because one of the other things we can do is to then look at this in map view. So this is another good example of data cleanup that needs to happen. So we've actually got two data sets in different there's data sets in map view here, but some of the data here actually have 0 entered as a northing. So they've got null data in the northing, so it's not plotting correctly. We can quickly deal with that by actually generating another filter. And what I'm going to do, this will probably get rid of my highlighted ones, maybe.
It should, yeah.
Yeah, but what I'm going to do is I'm going to quickly filter this out. And then we're going to turn them off. And by turning them off, we can now look at the data that we've got existing in the map view. I'm going to go back.
Worth pointing out, James, there's a warning down the bottom, because when you use the filter, I call it the super filter, it's like it doesn't exist a gas. And so that's why that red thing is down the bottom there.
The red
warning. So sometimes
here.
we get people contacting us saying, I can't see my data anymore, but they've filtered it out. And,
yeah. Yep. There's a few little warning things around the attribute manager that were really useful as well for knowing what you've done. So what I'm going to do is I'm going to actually go quickly. I'm just going to go quickly back, and I'm going to actually just going to plot our calcium. What did we have? Calcium, magnesium. I think it was the other way around. If I can think in alphabetical space, we'll just put magnesium on the X. So I'm going to plot that, and I'm going to again just use my flash highlighter. Oh yeah, there you go. Here, I did remember it. Good. Software programmers do good stuff sometimes. So here's my highlighted data, and again, going back to Dave's talk, we're now looking. We're going backwards and forwards between looking at the data and going, these are data points that potentially have a more calcite-rich signal to them, if that's our hypothesis. And here we can now see that data plotted spatially. So now we can see the spatial context to our data. And again, for you will know your project, you will know what that means, and you might look at that and immediately go, oh, that's where I have a set of faults, or that's where I have a set of stratigraphic boundaries, or something like that. I mean, there's certainly spatial relationships there of those highlighted data points that we're seeing in the map versus the diagram. So one of the other things that GAS really allows you to do very quickly is to ask these questions and answer them, and then start to use that to further refine how you look at the data. So that's been a really nice example of the way that we bring this kind of data in. If you want to then turn this, if you're happy that you've pulled something out there, you want to retain that, we can then attribute it more permanently as a color, a shape, or a size group. So color in this case. So we can, over here on the right hand side, we're using this diagram here. Oops. We go over here. We go apply attributes to selections. So I think this will ask me for a new attribute at that point. Yep. So we haven't got a new color selected. So I go yes. It generates a new color for us, and it now colors those data points in. So they're now sitting there as a more permanent grouping that we can then go and do things with, and we can look at all sorts of aspects of the data related to that grouping. If you're really
James, that might be a good point, because this is typical of the rabbit hole you go down in GAS, because you start to learn things.
Yep.
And that's why we put the checkpoint system into GAS.
Yeah. Good point. Actually, I did have it on my run sheet, but because I'd gone off piste, of course. So up here, this is a good point, and I think I'm as guilty as everyone of sometimes forgetting to do this, and then getting an hour down a track of playing around with data set and absolutely failing to remember how I got to where I got to. So up here, we have the ability, we've got a gas file. So actually I haven't even saved the gas file yet. So I'll just save the gas file here. So so I'm saving now all of this as a gas file. So that's now saved. I can share that and someone can open it up, and this would replicate exactly where we're at when they opened it up. But what I can also do is I can save a checkpoint at this point. You can choose to keep the time and date in if you want, or you can add a label. This is the dolomite control. At that point, you can write whatever description you want in at that point. And that will save that checkpoint. And then at any point we can come back. We can open up ioGAS back at that point, and we can rename it. We can delete that. So again, really useful if you're sharing the gas file amongst your team, is that you can actually almost record your workflow through ioGAS, save those checkpoints, and people can come back and they can see where you got to, and they can see what's going on. So again, a really useful feature to bear in mind when you're playing around with big data sets. So that's all good. So there's a few things here on the right-hand side that we can look at here. We've got a simple XY plot. We can see here that we can do various things on this XY plot. We can show means if it's a plot where the data is clustering. We can show the means on there, percentiles. One of the things that I use a fair bit for data quickly is to look at plotting regression lines on here. So we can plot a regression line. Now, the regression line for the black data is probably useful. The regression line for the orange data is probably not that useful. But if we put that regression line on, and we can, again, we can choose, oops, let me just move that. We can choose 3 different types. Ordinary least squares. Least squares regress through the origin or reduce major axis. If we do that, and that black line there is probably quite a useful one. It will obviously tell us the ratio of dolomite, really is what it's telling us. Once you've done that with a data set, one that I find really useful is you can actually bring up the report, and it gives you immediately that slope and intercept of that regression line. It gives you some statistics if you're using it in that way. One of the ways that I use this stuff a lot, and I wasn't planning on going through it much, but it's definitely on my list to do more videos on this. I use the regression line plotting a lot when I'm doing QA/QC of portable XRF data, or looking at calibrations and those kind of things, because you can really quickly plot up all of your measured versus expected data as a grid, hit the regression line, grab the report, and you've immediately got your calibration curves plotted out for you. It's a great way of doing that kind of stuff.
Yeah, and that's specifically the reduced major axis regression.
Reduced major axis, yep.
Yeah.
Yep. So there's a set of things on there. You can put XY lines on. There's a lot of these are useful for that. So you can play around with these. We can look at plotting density. So for a lot of our plots, we can actually put the density contours onto our plots, and you can keep clicking it to make it more and more opaque. Again, a really nice way, again, of sometimes seeing that, I guess coming back to Dave's point about the human brain looks at the plot of data points and it sees an even scatter of data points along a line. But actually, when you put the density plot on, you see that actually there's a strong clustering of our data points at one end and a strong clustering of our data points at the other. And, for a data set like this, that again is probably telling you about the fact that we have 2 dominant end members in our system here, and a scattering between them, which is the kind of things we were talking about in our hypothesis earlier. So one of the things you would do as a geoscientist at this point is, what I would do is I'd want to be looking at other elements, other geochemical elements, to try and work out what it is that is dominating the composition of my samples down at this end of the plot here, where the 0, 0 magnesium calcium, and it could be, I don't know, we could have a look at that. But those are the kind of things you want to ask. One of the other things you can use density plots for quite easily is, again, if you we'll come back to our attribute manager and you go, well, I actually want to generate another group here. I'm going to make this I'll just bring my color picker. I'm going to make this blue. I'm going to generate another group here, and I'm going to put all of these data points in this population down here in that other color group. So I go over here, I select my polygon select tool, I draw my polygon around this data, and then everything in there is now sitting in that color group, and you can see where that is sitting on that map there. Again, fantastic set of coherency to the data. So as soon as you look at it spatially like that, you see coherency. So we're definitely dealing with one data end member there, and we start to get a sense that the orange values and the orange data points are scattered around the outside of these blue domains in various places. And then the blue domains here are these ones with the low magnesium, low calcium values. So one of our end members is certainly sitting in here. And again, we can do the same, generate a color group, quickly go through, and we'll just select based on our density, our other end member population, and we can see again on the map where that's sitting, and then everything scattered between, which actually isn't a huge amount of the data. Well, we can see here the numbers. Actually, the default's 487 of data points scattered in between, and we can see again where they sit within our map pattern. So just from that really simple analysis there, we've actually gone through. We've actually come up with a hypothesis about dolomite control. We've actually identified a couple of different end members, maybe related to rock type. And we've identified a set of points that seem to be drifting off up to high calcium, maybe calcified, that we've colored up as another group. We can go through, we can rename these if we wanted. We can then save those and save this data file. And then we've got that then as a map. So immediately we've gone through, we've looked at that data, we've cleaned it up, we've got a hypothesis, we've done some plotting, and we've got it in spatial context, which might absolutely at this point allow us to constrain where we go and do more work. So I think just from that really simple illustration of how to bring data into ioGAS, which is what this session was, we've now gone through and shown you the power in what 45 minutes, an hour there of talking. We've gone through and done something really very powerful with that data in one platform. So yeah, and again, you know, we could save that checkpoint at that point. We go, well, I'm really happy. I've got a warm, fuzzy feeling inside. I really like what I've done. And we go rock type map. And we save that checkpoint, save the gas file. And again, we can then send it off to our team, open it up. They can open it up. It replicates back to this point, and we can then look at that in different ways. So I think that's a really nice, example of what we're doing in some of this stuff. So I'm just looking down at my notes here about the kind of things we want to do. So that's the attribute map. And of course, we could also look spatially at this data in terms of the variable maps. So we've got magnesium and calcium selected. So if I want to look at the same spatial distribution and I just want to look at my magnesium calcium, so it's something commonly we want to do, we can quickly look at it like that. And again, we could export. So this is where we can start to then export this to third parties. So if we like the look of these maps, we can configure them. So we've got a rendering option here. We can choose various different ways of rendering it, various different color scales, depending on what we want to look at. Increasing, decreasing, different opacities. Once we've got these looking nice, we can actually export these out to some of our GIS packages. So you can export them as a KMZ file to bring it straight into Google Maps. You can take it into something like map info as a tab file. Or we've got connections through to things like QGIS and systems like that as well. So I'll probably forget all of our integrations. We've got a lot of them, but again,
James, I'm just jump in so with QGIS. So the next release, which is the perpetual 2 weeks away, will have a live QGIS link. So as you change the attribute manager and GAS, it will update live over in QGIS.
Okay. Yep. Fantastic.
So maybe an import exporters be connected.
Yeah, right. So and we've had this. So we've had this live link with Leapfrog for a while now. So with Leapfrog, you can have your Leapfrog project open. You can live link to the data in ioGAS. You can do stuff in ioGAS and see that replicated in Leapfrog. So what Dave's saying there is we're going to have the same thing with QGIS for GIS type analysis as well. It becomes incredibly powerful because even though we've got some great tools in here, to actually then be able to see the power of doing this kind of analysis within the GIS package you're using to plan your projects, to do the rest of the analysis you want to do, look at infrastructure, look at all of those other things, is really, really powerful. And it speeds up your process. You could then, really quickly be planning your soil program, all those kind of things. So yeah, that's the kind of map stuff there that I showed you. I guess one of the other things, and Dave talked about this again, is gridding. So we do have the ability to grid data. So I've got the magnesium, calcium data selected. Lots of options there for gridding. Probably chosen something. What have I done there? Something strange.
Oops.
Maybe that's.
I don't know.
Done something odd. Anyway, let's have a look. Cell size.
Ooh.
So Dave is writing this down just in case either I've done something strange or that this could be a small little glitch that needs to be fixed before this goes live. But we'll just say sort of 4 or 5 cells here. This might, of course, I may have overdone it now. I might have overcooked it in terms of that might take a while to process. So if you're trying to grid a high resolution, like I'm probably trying to do here, it will take a long time. Yeah, so actually I've run out of memory because
I think you're gridding half the world, James.
Yeah, that's
I think the problem is that I think the gridding tool's not picking up the limitation in coordinates from the
superset.
Yes.
Yeah. So remember, we filtered out some data that was sitting in a different part. So what's happened here is the gridding tool is not taking that into account.
Yeah, I just wrote that down.
We all learn stuff every day. Now, so you know what? That is a really good time for a cup of coffee. I'll just have to restart, I guess. So what we might do, and I'm just looking at the organizers chat window here, which I haven't been watching. So what we're going to do is we're going to take a 10-minute break. I think it's probably a good idea. Going to take a 10-minute break. I'm just going to grab just another drink. So I'll be 2 minutes, and then I'll be back in front of my computer. And I understand there's a few questions coming through, and we might be able to then work through some of those while we've got a drink in our hands. So we're going to do a 10-minute break now. I'm going to restart this, and I'm going to get a drink. I'll be back in maybe 1 minute with a drink in my hand, and we'll answer some questions. Okay. All right. Bear with us.
That's good, Henry. It's the right amount of chili. Yeah, if you're only depending on the parts of it's a little bit more tomato sauce. Do we have some that don't for the pizza that we're coming? It would have been perfect, actually. Yeah. We're going to do a double boil next time. But the chorizo is nice. Yeah, that's good. They're looking the white box. Sure. That box.
a word, I just pick a random one. That seems dangerous.
Multiple universities and multiple people working, and professionals and professional organisations. Yeah, good.
Right. Okie dokie. There's a few good questions coming through. Try and right. There's one here I could just see in the Q&A panel. I know there's probably questions coming from multiple directions. I've just happened to have the Q&A panel open here. So this is, I have a question. How can you cap, or how do you do capping in ioGAS? I mean, replacing outliers with an average value. Dave, do you know what's being asked there?
I would want to know why you would want to replace an outlier with an average value.
Yeah.
Unless it refers to over-range analysis where you get a greater than 10,000 or something, greater than 1%.
Yeah, maybe.
Type analysis, maybe that.
Yeah, so like a below detection limit, but for an over-range.
An over-range thing. Caesar, if you type a follow-up, we'll get to it. But yeah, replacing less thans is problematic. Replacing greater thans is even more problematic. So what, if the if a method is only good to 1%, which is something you come across with ICP type analysis sometimes in assaying, where they max out at 10,000 ppm and you don't have an overrange method automatically instigated, then I often give it a silly number like 10,001 ppm, just so that you know that that is a replacement value, right? I can't think of anything else sensible to replace it with.
Mm.
And in fact, it's a design of experiment problem, because if you're really concerned about that and you've got overrange, if that's the thing you're asking, if it's overrange, then you should have organised with the lab to swap methods to give you a value which is valid for greater than 1%. Sorry, I've got dogs and things barking in the background.
It's all good. I've got an old dog sat right behind me. Just having a look at some of the other questions that are here. Does ioGAS read AGS files? I'm not sure I'm familiar with an AGS file. I might need a bit of...
No, I don't know an AGS, no.
Not sure. Not sure about that one. Various ways of bringing data in to ioGAS. Like I said, you know, if it's a if it's formatted, you can even sort of copy and paste it in. We've got the pug online. You can bring it in through various ways. Open linked data from things like Leapfrog and stuff. But yeah, I'm not sure. We might need a bit of clarity on that one.
Certainly, data can go to and from Leapfrog to ioGAS, so you can over the ioGAS link with Leapfrog, you can send data to Leapfrog, but also back from Leapfrog into ioGAS, if that answers part of that.
Yeah. There's quite a lot here. I'm sort of just trying to read through, but also cognizant of time and got a few things I really want to try and run through. I kind of knew this might happen.
So someone's asking about students. So we provide a server license to universities for very low costs for an unlimited number of licenses throughout the university. So if you're a university student, please contact us. Often what happens is, man, gas is used in 90 universities, something like that around the world. So you might already have access to it, but not know it is another thing.
Yeah. Yeah, looking for, I guess I'm right at the end of this session, I am going to put some contact information up. So if you do want to get, there are various licensing options for gas. I see some questions here around it. Honestly, the best thing is just contact us, you know, wherever you are, and we can get you some price lists and then talk to you about, you know, what would work best for your use case.
Yeah, and I'm just helping out here, James. So drill hole data, yes, you can get that into gas, but it needs to be desurveyed and linked up, and then you can do the wavelet tessellation, which I think James will do.
Maybe.
Yeah, weighting and compositing is not in gas yet. But again, we're going right back to the start. If you would really like compositing and those sorts of tools in gas, email us, because every time we sit down and plan a new release, we take all of these requests into account.
Yep. So what I might do now, there is a bunch of stuff. So, I mean, I guess I'm hoping that the organisers, well, we've got a list of these questions sitting here. If we don't get to them right now or at the end, we'll try and go through this list afterwards and get back to the people asking them, or get back to the group with answers. What I really wanted to do is just go into a little bit more. I will save that one because that was quite useful. I'm just going to open up another data file here, this one. So this is, and I'm just going to show you some of the other kind of pre-canned. I really want to just show some of the diagrams really, and how you can use them and what they can be used for. So this is a data set. It's another whole rock data set. So you can see a set of elements here. This is already cleaned data. This is actually drill hole data. So if we just plot something like iron here, this has already been desurveyed. So we can see here we've got a downhole plotting function. So you've got grouping field hole ID, and the from and to interval set as your from and to depth. And then it comes up with a set of drill holes here. We can select all of those. So I've just got iron selected as my element. We can hit that, and then we see a fence diagram plotted. Right. So at the moment, we're not coloring it. We haven't done anything with the data. This is just the raw iron as plotted down hole on those 5 drill holes that exist in this data set. This is actually a layered mafic ultramafic, layered ultramafic system. So what I really wanted to do was to show you how you can start to use some of the pre-canned diagrams. This is another way of really jumping in with your data set and exploring the kind of structure and relationship of your data. So what we'd do is what I'm just gonna do again, we'll probably just do the major elements here, which is really useful just to have a look at what the data set looks like. We'll hit the SPLOM again just to see what we're looking at. And so what you can see in this data set immediately is that, as opposed to the other one where we had sort of some dominant trend and then outliers from it, what we're seeing here is, yes, we've got a cluster of data and some trends, but we've also got some clear clustering as well. So this is immediately telling us something about the nature of the data we're looking at here. So there are some trends in this data, either that be alteration or some petrogenetic trend. This is ultramafic rocks, and then some clustering. So some distinctive, probably lithologies or something like that. So if we look at one of these plots here, so we look at something like aluminium, calcium, for instance, we can see that there's definitely some distinctive clusters of sitting in this data set here, and some trends away from the main data. So again, it's always a nice way to look at the data together like this to see immediately what you're starting to see. What we'll do is we're just going to jump straight into the diagrams and start to have a look at some of the diagrams. So there's lots of pre-canned diagrams in here, and it's related to what element exists in the data set. Now this is another, I'm going to turn into Dave in a minute and start preaching from the pulpit, but this is another classic thing for many geochemical data sets that you get, depending on what method's being used, is that people seem to think that silica is the poor cousin and should never be analyzed. And of course, as soon as you don't analyze for silica in some kind of 4-acid digest method, then you're going to lose access to many of the classification diagrams that rely on something like silica as a dominant component. Something I will say is that modern portable XRF technology has actually become so good now that it actually reports silica really, really well. So if you're ever faced with a historic data set and a set of pulps, and you want to really kind of expand on the data you've got, something like portable XRF campaign on those pulps, pressed as pucks, to give you really good light elements, in particular silica, and very good zirconium, strontium, things like that, is a really good substitute for missing silica in the data set. So when we open up that classification diagram, you can see what's available to yourselves, to you based on your data set. So we've got the major elements here, and I'm just going to look at something like the Jensen cation plot in this case. And so here's a pre-canned diagram. You can see that diagram looks quite nice. You've got the reference back in the menu there, and you can see how our data is sitting on that diagram as it sits. So here we're plotting cation percents. Again, one click of a button, my ppm data is being plotted as a cation percent ternary diagram. There's various things you can then do.
And that's not to be underestimated, James.
Yeah,
because, I don't think I would go out to Excel and get that calculation right myself to plot it, even then to plot it somehow.
Yep, absolutely. Yeah, I mean, I guess I'm so used to using ioGAS now, I forget that some of these steps were so painful before. So this is most of the data here is sitting in the Camata field in this particular data set. But one of the things you can do, if you've got a diagram like this and you want to then classify your data, against those data points against that diagram. Is a really simple way of doing that. If you come over here to the menu, you can see here there's a color rows by polygon, and what that does when we hit that button, it then gives you the groupings from the diagram based on your data points position. So we've now classified our data. Yes, dominantly it's Komatiite, but we've now classified that data based on it, where it falls on that diagram. So you can see here how if you've got a classification diagram related to geomet, related to mineral chemistry, related to something else, how you can then use that, and as you bring new data in, if you're happy with that diagram for your project or something like that, you can bring that new data in and plonk it into there and classify it really, really quickly. So that's a really quick way of doing that. Once, of course, we've got a classification like that, so we've got a few high mag tholite basalts, few komatiitic basalts here, we can then go back. We can just select, if I just select one element again, select iron, and we'll go back here to the downhole plot, and I'll plot those drill holes again. One of the things you'll see is that those classifications are now sitting here in the drill hole. Now, it's a pretty boring one. We'll find a more interesting one in a second. But we can see now, again, coming back to that spatial aspect, we're now looking spatially in a sense of downhole relative to that fence line of drilling, where those different units are sitting. And we can see some of those different units sitting within the drill hole. So that's just a way of using diagrams very quickly like that. We could also look at something more complicated. So look at a nickel exploration diagram here. There's a few different ones here. I'm probably going to show myself up to all the nickel experts out there about which one I choose to do something with, but you'll get the idea. So we'll just look at something like, let's look at something. I know these are not komatiitic flow rocks, but for the sake of it, we'll just have a look at something like a diagram like this. So this is again a really classic example of an academic diagram from a publication. It's Steve Barnes's work that's been brought into ioGAS, and you can see here how we've absolutely translated the boundaries that existed in the academic publication back into this work. Now, these rocks don't exactly match in with this work, but you'll get the point, is that you can take a complicated diagram like this, and again, we can, delete all of those classifications, and we could color up our data points by the classification in a diagram like that. So there's quite a complex diagram. And again, we can look at our downhole plot and see where in those drill holes those different classifications are existing.
James, that Steve Barnes plot is a classic example related to the question earlier about bringing in reference data and comparing your data against it. That's a classic use case.
Yep. Yeah.
It just happens to be published, but it doesn't have to be.
Yep. Yeah, it's a good point. Good point. So and again, if there are diagrams you want to see, let us know. Other diagrams, and so you can see the kind of things that we have. We have a lot of inbuilt ones here: nickel exploration, alteration vectoring. The Davison Whitehead, it won't particularly work for this because these are the wrong types of rocks. But yeah, so dominantly sitting down in here because we're not seeing a lot of these white micas in here. But you can see that quite comprehensive diagrams are built in, and it's very, very quick to then plot those. I didn't go and calculate the molar ratio of potassium and aluminium there. ioGAS did it in a matter of a few seconds. And one of the nice things about ioGAS calculating those ratios with the diagrams is that those ratios are then also added as derived values at the bottom of my selectable list. So I can now actually go and start to select some of these calculated parameters or derived values that have been calculated as part of those diagrams. They'll start to appear here. And so we can choose to write those back to the data file. We can then use those to plot our own things. We could plot, some of those ratios downhole, for instance, something like that. And again, for the spider plots, it's something similar. We could again go and look at something like, some of these normalization processes here. And again, I'm not sure again what this data set has in it, but we could look at, the 1995 C1 chondrite normalization scheme. Doesn't have the right data in it, fine. Let's look at maybe the nickel copper PGE normalization. So there's just a normalization, a published normalization scheme, and you can see now our data plotted relative to that normalization function. And we can do various things again once you've got that diagram highlighted. And again, I'm kind of really showing you this quickly because it's really a case of going and playing. You can then change the visibility of this a fair bit. So we've got 3 color groups there or so captured in this data set right now. We can look at kind of the statistical mean of those color groups. We can look at the percentiles. We can turn those on and off. So we can get this, we can get this working or looking like we want it to look like. So we'll just do the central. There you go. So there's the central percentile. We can change the order. We can make that look as nice as we want it to. So we can see what our data set looks like relative to those normalizations. There's a lot of normalizations built in here. Like we said, we've got things like the human body, iPhone 3, if you so choose. But a lot of the rock type ones, chondrite, mantle. We've also got, so we can look at something like primitive mantles. If we had the right elements, we don't have the rare earths in here. We've also got, so again, coming back to the QA/QC thing I talked about earlier, one of the ones I use a fair bit of, we've actually got some of the Aureus and Geostats CRMs built in as spider plots as well. So if you're bringing in your portable XRF data, for instance, you've collected a whole series of QA samples and you want to see the performance of your program relative to the known CRM, you can really quickly plot that data against the CRM there and see whether any of those elements are misbehaving relative to what they should be doing and whether they would need a calibration to bring them back into line. So there's lots built in.
And you can put your own reference rocks into them.
Yep. Yeah, absolutely. So if you're using your own internal reference standards for something like a portable XRF program, go and put them in. And again, you're going to get report quality diagrams out of this very quickly. So it does help with your reporting workflows. So I think that was just a quick foray. We've been going through this as a quick foray into the world of diagrams, into the world of what we can start to do with data like this. Just to give you an idea of what you can do, and it really is just a case of go through and explore and understand those different menu items. And we've looked at rock nodes, we looked at that earlier. So with the rock nodes, the mineral nodes, you can do minerals, you can do rocks. There we have standard reference rocks built in as well. Lithological diagrams, I've shown those, sploms, density plots, regression lines. So I think I've gone through a lot of that in those 2 little sessions there. The reason I want to kind of try and move on a bit is what I was keen to show you was some of the structural analysis as something a little bit different from just geochemical data. So what I'm going to do is I'm just going to open up again another data set here, structure. So I'm opening this up. This is a data set. So now so there you can see I opened up a GAS file and it has actually restored that GAS file to the way I left it when I left the file. And what we're in now is we're in the structural analysis menu here, where there's a set of items we can use. So this is structural data, dip direction data with some metadata associated with it. We can look at the data set. If we just click the data here, we get the data table. So we can see what's here. We can see we've got some gold ppm data here. We've got vein type classifications. We've got vein width information. We've got dip and dip direction and some free text, because geologists can never help putting a bit of free text against anything that they log. And then we've actually got some desurveyed points as well. So we've actually got this data in 3 dimensions. So what I'm looking at here is a StereoNet. What we're actually looking at is a StereoNet colored with respect to the attribute manager. Now, when you first plot a StereoNet in ioGAS, there's a little configuration tool down in here. It's a good tip for you, StereoNet settings. And you can choose to either have the StereoNet plotted with the data from the attribute manager, or if you don't have these ticked, it will plot it with its own structural symbols. And they are symbols related to the type of structure that's plotting, be it a lineation or a plane, a pole to a plane. So if you're just doing structural analysis only, and you want to just work on it with just structural symbols, then don't tick those. If you want to start using the power of the attribute manager, then just make sure you say use attribute manager symbols and size in plotting on my StereoNets. What of course is immediately means we can do is we can start to do some really fancy stuff with our structural data. So what I'm looking at here is poles to planes for a set of planes here. We can see here the different geology logged classifications of those. So I can turn a bunch of those off, and I can just look at, for instance, breccia veins in this instance here, and we've got the breccia veins. Now, what you'll notice in the data set is we had a gold assay value associated with this data as well. And what's happened there is actually probably compositing. We talked about compositing a minute ago. We've actually composited the data from the geochemical data and from the structural logging data. We've brought that together. We've integrated that data. Probably in this case, it's probably using Leapfrog's compositing tool and then exported it out. So we've now got a gold assay value associated with my structural reading. And so we're coloring here by vein type. So we're looking at our breccia veins here. We can see that we've sort of got a bit of a girdle of data here, but a lot of our data is sitting in one place here on our StereoNet. And one of the things we can say is, well, is there a relationship now to orientation and something like gold grade in those breccia veins? So one of the ways we can do that is we can just go to our attribute manager, select size, and just go down here and select gold ppm. We'll do progressive. We'll do something like this to really highlight those high values, and we go auto attribute. And what that does then is it auto attributes our data relative to this schema here. And we can see here now immediately we're looking at structural data, but we're now looking at the distribution of our high grade gold values relative to our low grade gold values in those breccia veins. We can start to turn on our other veins here. We turn those on, that's the bulk of the data set, and we start to get a sense that actually the highest grade gold values do tend to congregate or cluster around the steeper orientations of breccia veins, not so much the flatter ones, although there is some scatter, as there always tends to be in this type of data. So it's really interesting from the point of view of starting to ask those questions, those kind of questions we've been asking for geochemical data. We can now ask them inside structural related data as well. And by bringing in different metadata, we can then ask that in a different way. You know, one of the things we can also do, of course, is we can go backwards and forwards between our normal XY plotting and the StereoNet as well. So we can start to see the spatial aspect in the structural data and the StereoNet. So one of the things we might do here is we're going to select gold grade versus width, and we're going to plot that as just a simple XY plot. And we can see here it carries through those attributes that we had, and we're just going to log that along the gold axis there so we can see what's going on. And we can see that we do have some wider or thicker veins here. And again, we could use something like our flash highlighting tool to quickly ask the question about whether these thicker veins are sitting in, thicker gold bearing veins are sitting in a particular orientation or not, or whether they're spread around a particular girdle or something like that. So we can, again, by attributing our data and moving backwards and forwards between these two different ways of looking at the data, we see the data in different ways, and we can ask different questions of it. If we just go, so I think we said this is actually spatially located data. So one of the things we can also do is then look at this data in 3 dimensions as well. So I'm just going to turn that off for a second. Actually, I'll tell you what, I'll make that a color group. I won't. I'll make that I'll turn that off. And then we can, in the 3D plot, we can then spin that and start to see, again, in drill hole trace sense, where those thick veins are relative to everything else. So, you know, we could, we're looking at, I guess, 3 different views of this data right now. We're looking at the data in terms of its numerical relationships between gold and width in this case. We're looking at the data in terms of its 3-dimensional relationships to each other. And then we're looking at the data in terms of its structural relationships to each other, whether it's steep, shallow, whatever that structure is. So just from having those plots across the screen there, we're looking at that data in 3 different ways and being able to ask questions. So if we wanted to just go back to my stereo net, and I might just contour, just trying to think of a good way of doing this. Probably not that. What I might do is just put, for the sake of, no, I'll tell you what, we'll just grab, I know what I want to do. We'll grab the flash highlighter. I'll just kill what's there, and I'm just going to, I want to look at this data down here because I'm interested in this orientation of this data. And so I highlight that. I can see where that data is sitting on a graph like this. And of course, you could have lots of different geochemical parameters in here. And we can also then see that same data, that same data in 3D. We can see where that is spatially in 3D. So being able to kind of move backwards and forwards between those things is really, really useful. And that's one of the real powers of ioGAS and our ability to look at the data in different ways. It's also really powerful in terms of starting to take structural data and integrate other data sets to it, other metadata sets to it, to be able to understand what's going on. One of the projects I've seen before is people using, again, portable XRF to measure vein chemistry. So you're associating a portable XRF analysis and vein chemistry, point vein chemistry of the structure that you're measuring, and then being able to put it into a system like this to work out the chemical and structural controls on where your grade is deporting. If we just go back to this, so we just turn the flash highlighter off. We'll just go back to the breccia veins in this instance, and we can see some sense here on the breccia veins, maybe even on the veins themselves, some sense in the breccia veins of a girdle distribution of those poles there. And there are various tools here for exploring structural relationships as well. So doing structural analysis. We can show the means of this data and the kind of error ellipse around it. And if we keep clicking through, we get various different ways of looking at that. One of the things that you can do is you can put in a Bingham great circle. So you can fit a great circle to this, and it will give you a fitted great circle and the beta axis of that data. So if you've got things like fold data, things like that, you can then put that data into something like this and do this kind of analysis. For anything you do, again, you can bring up the report and it will give you the results of that analysis as well, which you can then copy. One of the new things that's coming in, so this isn't limb data, but if we just assume this is limb data on a fold right now, we can actually, for this data, we can select data on 2 limbs of a fold, and it will give you an estimated axial plane for that fold as well. So I am kind of stretching it a little bit now because this isn't exactly that data, but if we just select some data over here that we say is on 1 limb, and data over here that might be on another limb, and it will basically use that and analyze it and give you an actual plane that it's giving you an estimate for here. So there's some quite advanced analysis methods now built into the structural part of ioGAS. And I think to embed that into the power of how we can use attribution and how we can bring data in from other places is really, really useful. So I hope that people find that very useful. So again, just go through and play around with these. There are tooltips available. There's help in the help manual for all of these, but there's a fair bit going on in the structural tools. So I was just keen to touch on that, really, to show you what potentially was possible. You've even got some, I noticed some fancy ways now, Dave, of spinning the data around against the trace, the stereo net and that kind of stuff.
Yeah, it simulates the tracing paper on the stereo net that you can do. Yeah.
Yeah.
It's turned into an excellent teaching tool for structural geology as well now.
Yeah.
I don't pretend to remember all of that either.
So there's a lot in here. You can, it's probably worth just pointing out the fact that you can put user planes on here. So if you're doing analysis and you want to manually put a plane on here, or there is a plane that you want to put on, so if we just put a plane on and we'll just configure that, there is a certain plane you want to put on. So for really interested in any geotechnical people in the audience, be really interested in your take on the kind of functionality you might like to see in here. So here, this might be that you want to put a plane on here related to your slope you're building, or something like that, and you want to see that relative to joint faces, understand whether you might get wedge failure, that kind of stuff. So we've got those kind of things in here. What you can also put on here is you can put drill holes. So you can actually put a drill hole. So if this is drill hole data, you might put a drill hole, your drill hole orientation on here, or mark it on there. And why that's really useful is that this little tool over here, fit small circle. So if it's not going to work here because this isn't a small circle distribution, but if you had a data set where it was distributed around this small circle and the mean of that small circle was equivalent to or close to the location of the drill hole in space, you would then question the quality of the structural data, because it's probable that you've got core spin when you're bringing that orientated core back out of the barrel. That will spin in the barrel and you're getting poor orientation of that core. It will tend to ascribe to a small circle. So those are the kind of workflows that you can not only analyze your data, but also you can start to do QA of the data as well. So a lot of really useful tools in there. Really keen to hear from people on how they might use this and how they start to use it in their different applications. As you can see, we're starting to very much move beyond just geochemical data into other data types in this way. Okay, so that's the structural stuff. I think we've touched on a few of these other things. So given that it's 12:05, what I might do is I might at least do one or two. I've got a couple of different ideas on workflows here. And I know Dave's chucked one at me about the wavelet, and I'm going to have to think about that one on the fly. And let's have a look at what I've got here. So what I want to do really now is just to start to look at, I guess, multi-step workflows and how you might take a data set, having done the kind of things we did earlier, then start to apply analytic routines or analytic algorithms to it, to then try and automate the way that you pull out patterns in that data set as well. So I think, so Dave, one of your data sets I think I grabbed from Fred the other day was the Gossan data set, which is a good one. So I'm just going to open. This probably has a long history to it, does it, Dave?
Quite long. Collected as part of my BSc honours project, so yes, quite long, very long.
That's good. So for undergraduates or graduates in the audience that haven't played with ioGAS, you can see there that you know, for your project work, doesn't matter what you're doing, you can start to use ioGAS. And actually, just as I just reminded myself, there is actually some really neat ways of using ioGAS to analyze microprobe data as well. So something I've been playing around with a bit. You can use principal component analysis in ioGAS for microprobe data to start to look at exchange vectors and things like that when you're using it. So for anyone working in that kind of data, there is ways of using GAS. So this is data collected for, I guess, it's the Gostons sitting above a set of deposit types or rocks and analysed whole rock geochemistry. So what I've got here is you can see the Cypress type, epithermal type, iron skarn type, and Kuroko type classifications. These are already classified because we know where the samples were collected in this sense. But we've got a set of data here, 8 data points where I've unticked those. They're filtered out at the moment, which have a question mark, and we kind of want to know they're collected, you know, nominally across the deposit where you don't know what it is, and you want to know where that fits relative to those other deposits. This is geochemical data, so we've got a set of small number of elements here, and you see that I've selected a subset of those elements. So I've already done a bit of work here because actually I've gone through. If I just go through and I'll pick up the more complete data set here. Actually, I'll put everything on. What I did was I came in and I probably did something like looking at the probability plots here of all of this data, and I went through and I looked at this and I said, well, it's mostly log normal, but we've got some problem data here. This is classic stuff you get. So we've got some data here where large proportion of the data is below detection limit. We can see that here with this flat line. See that for tin. We've actually got a repeat of gold, I think, in here as well. There's 2 representations of the gold, one in ppm, one in ppb. So we don't want 2 of those. So what I've gone through and I've done is I've cleaned up, taken some of those elements away, cleaned it up. And so what I'm using here, this little drop down here, is a history tool. It actually allows you to go back to previous selections in your session. So this is, again, really useful if you're kind of diving around, you're trying different things, you're taking elements in and out. You can actually go back and go, oh, okay, I want to go back to selecting everything or selecting that group of elements. You use the history tool. So here we are. We're going to select this set of elements to look at our data. It's not too bad. The lead is some stuff below detection limit, but it's not all of the data, so it's probably not too bad. And we can see here by clicking the log button that all of our data is pretty well log normally distributed in this sense. So when we're doing certain things to the data in the analysis of it, we want, you know, a lot of analysis routines like our data to be normally distributed in some way. So we tend to recast our data to make sure that it is. So what we can do is, one of the things we can do is we can just have a look at the data, just plotting it on our XY plots. Again, we'll just log the 2 axes here. We can start to see that we've colored up our data based on the type of deposit type it was taken above, and we start to get a sense that the data is clustering or grouping. But it's very difficult to see that any one element or any one plot is doing a comprehensive job of pulling apart those different groupings. So we do want to then take that data, which is now in a, how many, 9 or 8 dimensional space, and we want to then try and pull out our data relative to all of those elements at once. And that's the point at which, unless you are some kind of super genius, it's very difficult to do that with your brain. Okay, to visualize that, to look at that in n-dimensional space is quite difficult. So I think what we'll do is we'll go to the analysis menu, and as I said, it kind of starts off with basic stuff and it goes more and more scary as you go towards the right here. But what I'm going to use in the first instance, there's lots of different methods actually with this data set that work really, really well. But what I'm going to use is a discriminant projection analysis. Now, it's always very nervous trying to describe what a technique does in front of someone like Dave and probably other people on the call that absolutely know what they're talking about. But really what discriminant projection analysis is doing is it's taking your groupings and it's taking your data and it's trying to sort of minimize or simplify the number of algorithms it uses to pull apart that data into as many or sort of into as fewer clusters as possible, but to cluster the data and then minimize the variation within the clusters. So it's going to use all of those elements and it's going to generate vectors. And we're going to start plotting the data in chemical vector space. So if I just run the analysis, so we can pretty well take what's here. We know we've got 4 color groups here in our plot. We've got 10 variables. We know we want to log transform our data because we want it to be normally distributed. And we run that. What we have here is it comes up, it runs that analysis, and we've got a set of our summary data here. We can see the count, the number of samples in each of the groups. We can see the weighting of the elements against those different groups. And if we look down here, one of the things I tend to look at is it basically pre-populates our calculation column here with the chemical vectors that it's created. So here we can see these are chemical vectors with using all of our elements here. You can save these. You can save this as something you can reuse later if you so desire. But one of the things I look at here in the notes column, it actually shows you how much of the variation in the data set is described by that chemical vector. So it's a good way of seeing that you are describing a serious amount of the variation that we see. So I'm going to calculate those, and it's going to calculate those parameters. It's going to save those. I won't bother saving it because I know how this works. And you can see here I've got them selected. So these are now chemical vectors, and I can plot those. And we can see immediately that we went from a sort of a matrix space to now, if we look at just the first and second chemical vector plotted alone, we can see that our data points are sitting in very distinctive groups. So these are quite complicated chemical vectors here, but we are able to then use that to classify our data. Now, hopefully I calculated those chemical vectors for all of my data, whether it was turned on or off. Now I used the turned on data to calculate the chemical vectors, but what I'm going to do now is I'm going to turn this unknown set on. I'm going to make it yellow, I think, just to make it stand out a bit more, yellowish. And I'm going to turn that on. And you can see on this chemical vector diagram, immediately you can see that that data all sits within a single group here, which is related to the Cypress type Gaussians. So if we were going out there, collecting some unknown samples, just using that process alone, we can get a really good sense that those unknown samples we've collected are related to that particular type of deposit or deposit type, and just by doing that. So that's discriminant projection, and then you can save those chemical vectors. And the nice thing about saving that function is that when you bring new data in, you go out and do some sampling, you bring new data in, you can just apply that function to the new data and classify it on this diagram. Now, one of the things you could do at this point is you could say, well, I actually really like that. I want to save that. I want to use that. I want to share that to other colleagues. So one of the things you could do is you could get a polygon tool. You could start this as a diagram. You can get a polygon tool. You can hand draw lines on here. This is the academic approach. Hand draw lines on here and create boundaries. Now, one of the other ways you can do that in a more automated way, more statistical way, is to use the auto domain tool here. So this is a tool, again, it's a supervised method. So again, we're using the classification we already know. I'm going to turn those ones off. and we're gonna draw those boundaries on there. So I've got DP1 and DP2 selected in my elements selection, and I'm going to plot that. And then what that's doing, and Dave, you might have to explain this even better than I can, but it's plotting the statistical median point between the cluster means. Is it not?
Yes, and it's taking group, because this is using covariance, so it's taking in the group shapes into account, so the boundaries are not linear, and that's why they look a bit weird. So it's actually based on the Mahalanobis distances between the points and the groups in that 2D projection. Anyway, what it's done is it's automated a best possible way of drawing a classical geological classification diagram.
Yep.
But it's far more, I tell you, what was done there is probably far more rigorous than many of the things that are published in the literature.
Yeah. Yeah, I think, and so you can then, now you've got this diagram, you can then, where you can tweak, there's various tools, drawing tools over here on the right hand side, you can tweak the boundaries if you so desire. But I mean, I think as Dave points out, I mean, this is what you've done here is you've let the mathematics decide based on the data, based on the groupings, based on the clustering, you've let the mathematics decide where those boundaries should be. And so you've taken subjectivity out of it. And what that then means is that you've got reproducibility. So if you took that same data set, you ran it through the same algorithms with on a different computer, you get the same result. So you're not relying on a person with a pencil drawing those diagrams. And you know, in the back of my mind, at some point when I win the lottery and I'm sitting here not having to work anymore, I have thought about, you know, we should probably go back through some of our classical petrogenetic diagrams and run the same kind of analysis actually with the same data to actually get much more rigorous and numerically correct boundaries for those diagrams, rather than wiggly diagrams drawn with a glass of red wine in one's hand at 1 o'clock in the morning when you were finishing a manuscript off. We've all done it.
Yeah. And the other thing, James, is you can, if you save that diagram now, it saves the entire linear equations that project the data onto DP1 and DP2 and the boundaries. And so if you bring in a new data set without any other context whatsoever, but you want to classify it on that, you can just bring it in, open the diagram, and go back.
Yep.
Do that in R or S+, or even Python. You know, they can do elements of this, but to do it like that, they just don't do that.
Yep. It's the workflow. And it's the ease of the workflow and the ability to share the results. So if you save this as a diagram down here, you can save these diagrams. You can save it as a diagram that can then be brought in, and you would find it then under the user diagram menu here. And so then again, you can share that amongst your team. They can open it up in their version of ioGAS. And as Dave says, if the data is the same, or as long as it's got the same list of elements and stuff like that, everything's there. The vectors are calculated automatically. The data is classified automatically. So, you know, use cases where you're taking a learning data set and generating something that is then used on new data over and over and over and over again is a very quick way of doing it. So that's discriminant projection and the ability to take discriminant projection result into a diagram. And so actually, I guess just before we move on, if I then just, for the sake of it, save, what I'm going to do, I actually save a checkpoint. This is quite unlike me. Okay. And then what I'm going to do is I'm going to turn this unknown on. It sits in here. If I now want to classify that, all I would do is I would go color by polygon. Yes, and there it goes. That data has now been reclassified against the Cypress Neo. So we'll just close that and close that now. Let's just open that. Yep. So you can see how I opened that checkpoint and I've gone back to having my unknown sitting there. Just keeping a check on the time. So there are a few different ways. Like I said, there are a few different ways of generating classifiers, I guess. One of the other ways we can do is to use, again, in the supervised learning method, we can use a classification tree. And what the classification tree does is it will take your set of elements. So we'll go back here, we'll select our set of elements. It's going to take the set of elements and it's going to generate binary decision points. And it's going to go through and it's going to start putting our data into different buckets until it's got to a point where it feels it can classify the data into those groupings that we have. So I've got those 4 groupings switched on. I'm going to select the cart here, the classification tree option. I can use the color groups, or I can use the deposit type. It doesn't matter, we've got the same. I'm going to select the default here, default split rules. There's a lot of options built in here. Again, go to the help manual for ways of playing with the options. And what I'm going to do is I'm now going to automatically partition my data set into a training data set. So it trains the classification tree, and then a test data set where it puts data back in and tests it out. So I'm going to do that. Stratified sampling, what we're going to do is we make sure that when we pull our percentage of training data out, we're pulling it the same percentage out of the different groups. If you haven't, if you've only got one group or something like that, you want to pull it randomly out of your data set, don't turn that off. But if you want to pull out the same 70% out of all the different groups you have, click stratified sampling. And then we're going to train that tree, and it's going to go away and it's going to build us a classification tree. So here's our classification tree, and you can see the questions that are being asked and how it's classifying. So we can see that it's classified the data like this. It's telling us that it trained at about 98% or 97.7% accuracy, and its test accuracy is 100%. So it's a pretty good result. And so what it's doing is it's bringing the data in. It's saying if ppm is less than 4150, it goes down this branch. If it's false, it becomes Kuroko style. And it just keeps asking that. So we've got 3 questions being asked. So one of the things you'll notice, so if we just go to the report, one of the things you'll notice immediately is that we had 8 or 10 or something elements. So we put in because we thought they were all important, but actually we've been able to get an incredibly high class classification out of only 3 of those elements. So it's really only taking 3 elements there to generate that classification. So, you know, in a sense, for if this was an ore processing problem, and you did a benchmark study where you chucked everything at the samples and you generated a classification for how your ore was going to classify or process or something like that, and you went through that exercise and realized you only need to analyze for those 3 elements, then that could be a decision you make, that you actually only analyze for those 3 elements because you're only using it in that one way. So it's a good way of looking at the importance of the elements. We can also look at the confusion, what's called the confusion matrix, which tells us a little bit about the performance of the algorithm. So this is the predicted, this is the training data, this is the test data, and it tells us whether or not stuff was misclassified. So here in the training data, actually some of our data here did get misclassified, one sample in both, but you can see in the test data everything got classified correctly. So and there's various ways of looking at that. You can look at that as number of samples or percent of total. So it gives you an idea of the accuracy. So these are different ways of illustrating how good my classification has been in this sense. Go back to the classification again. There's a couple of things we can do here. So we can, again, like anything in ioGAS, we can save this as an XML file in this case. But what that means is we can then read that in and use it for new data. So we can save that, share it in our team. When new data comes in, we can classify it straight away. One of the other things we can do is we had some data that we kept as invisible. So we turned this unknown data off here. It wasn't used to build this tree. But if we now go back to the tree, what we can do is we can say, run the tree on all the invisible rows in my data set. We click that button, and what it does is it says, actually, all of those samples in my invisible data set are classified as Cyprus NEO. So yes, the same result as our previous investigation, but now using a different method to do that. So that's just an example of the kind of thing you can do with supervised learning, where you've got pre-existing classifications and you want to then try and understand how we can replicate those with our numeric data. So this could be that you've got lithological classifications, you've got whole rock data, and you want to generate a classifier. You can also do a regression tree classification, which is where you're trying to predict a numerical outcome. So you might be predicting the gold grade in a set of data, and then you can use the same kind of process, but now our outcome is gold grade, high, low, medium, whatever. So all of those are built in. One of the other things we can do is, so if I'm going to turn all of the groupings off here, keep the deposits filtered. I'm going to got those elements selected. I'll just plot those. So this is the equivalent of coming in with a set of data that you might not know the groupings for. And so now we go, well, are there clusters sitting in this data? So one of the things one of the most basic things we can use, of course, is the k-means clustering. So we can do k-means clustering here. So this is an unsupervised learning method. So right now we are letting the data inform us about how it wants to split apart into clusters. And the beauty of this is that it's doing it across that 10 elements, it's doing it across that multi-dimensional space. So again, something your brain struggles with. We see bits of pattern here and there, but to be able to kind of look at it across that whole n-dimensional space is really hard. We can use methods like clustering to do that. So we go in, k-means clustering, we're going to do a log transform. We know that was something we wanted to have in the data. We'll do that, we click OK. And there's a couple of things here. We can see that the bulk, so what we're looking at here is some of the squares. So that is the sort of the distance, it's how lumpy the data is and how far apart the clusters become, basically. And what we're trying to do is minimize this. Now we can see that we do get a couple of different drops here. But, really our biggest drop we're looking at here is around 4. And we know that in this data, we have 4 clear groups here. And we can see our biggest drop. So we would select 4 as our number of groups. We're going to apply that to a color label. And we can show our discriminant projection plot again. So we apply that. We overwrite those DPs, yes. Here's our discriminant projection plot with just the k-means clustering. We see 4 groups pulled out. These two kind of overlap ever so slightly. We can see how we've colored up all of these different groups here. So this is just a way of, now we are looking at the groupings, but now we're looking at them based on how the data is clustering, not from a pre-assertion. So here we didn't know about the groups, and we're letting the numbers, or letting the data tell us about how the groups might fall apart. So we can see it does a pretty reasonable job in doing that. And again, you can go from this point, once you've generated a classification like this, you can then go and start looking at, for the different elements, where those different groups are sitting. So we can see here high manganese, high iron in this orangey group. It's got lower copper. So you can then start to go through, so higher lead in the green groups. You can start to go through and say, all right, now I've got groups. I now figure out what those groups relate to. So that's just a way of using k-means clustering to do that. So that's quite a simple data set. But you can see there I've used a number of different methods to then try and find the patterns, find how the numbers themselves are falling apart in that data set.
James, you could just press the parallel coordinate plot at this point.
Parallel coordinate plot.
Graph.
There you go. Parallel coordinate plot is, where is that, Dave?
No, I'm pointing at it. You just went past it. No,
Oh,
right.
Oh yeah, there. Okay.
Yeah. No, that's the line plot.
Oh yeah. Oh, there you go. Sorry. Right.
Now log that.
And log that.
And that gives you a great summary. So if you've run a k-means cluster and you're wondering what the contributions of the input variables are to the separation in the clusters, that's a superb method of visualizing that.
Yeah, it's a good idea. And so it's actually quite good for everyone in the audience to see there that, and actually I made a note to Dave last night or this morning, I think it was, that there is so much packed into ioGAS. There is so many different routes to finding different things that actually just for us two working together like this, we've found different ways of looking at it. And so it is one of those bits of software that actually it's good to work on by yourself, but actually there's a real power in actually getting other people to have a play with it, because they might find different ways of doing things. You can't break anything, so just play.
Oh, no, so that's another thing, right? Despite what I said right at the start of this session, we never discourage people from pushing buttons. So it's not writing back to your corporate database. You're not going to blow up the space shuttle on the launch pad or, anything like that. So press the buttons, have a look, press other buttons, and then read the help file. There's another way of learning. It is an exploratory environment, there's no doubt.
Yep. So I think that's a really good introduction to kind of the unsupervised learning, and we've shown you different ways of doing it, from pre-existing classifications to not knowing anything. So what I now want to just show you, I'm just cognizant of time, and I want to give people a little bit of time right at the end we'll just try and grab some of those questions. But there is a lot to show. What I just want to do is I want to open up another data set, MSDP portable XRF. So this is actually a data set. This is a consistently collected data set of portable XRF data. This was a regional drilling program done in South Australia, but the data has been collected in a very consistent way here. Consistent sample preparation, consistent machine, a lot of QA, QC. I'm going to show you 4 drill holes here. So what we've got here is a set of data. So again, what I'm going to do is I'm just going to plot it like this. And so this is looking at portable XRF data, and this is a good example of where you do consistent sample preparation and consistent portable XRF use. You can actually get very high quality data, including silica. So looking at that data plot there, I'm just plotting silica against a bunch of the major elements. What we can immediately see in that data set is that there is distinctive trends, distinctive groups. So this data is showing us some structure that is definitely related to something real. We're not just seeing noise there, we're seeing something very real. So we want to try and unravel that a little bit. Now, one of the issues with portable XRF data and whole rock geochemical data is that we have this problem of closure. That is that the analysis typically sums to 100% or close to 100%. What that means is that as you take or add mass to the sample, you might leach or enrich certain components, you can get weird false effects where you get a sort of a anomalous, say, silica enrichment just because you've taken other stuff away, not that you're enriching silica, right? There's this weird closure effect. So one of the ways you can, and people do argue about this, one of the ways you can get around that is to do a thing called a centered log ratio analysis. Now, I'm not going to go into the details here, but this is one method a transform of your data that is designed to try and remove the effect of closure and get back to the actual effect of mass transfer in your samples. So I'm just going to hit that. So this is actually a really complicated algorithm it's running, but you hit that, and now we're going to plot that data again, and it's got the centered log ratio values here. Look, plotted. They're numeric values. They're derived values. We're going to plot that same plot, and now we're looking at it as centered log ratio. We're getting rid of that closure. We get rid of some of that trend, and it tends to clump or cluster the data a bit better. One of the things we can do when the data is looking like this is we can just put the density plot on, and immediately we're starting to see that our data is falling out into really distinctive groups, right? And just with that density plot on. But again, it's a very complicated pattern. We see complicated patterns across multi-dimensional space there. To be able to do that in a manual sense is very hard. So again, we can go back to our analysis. So again, we don't know anything about this data other than what we've drilled through as a geologist. We can go to the analysis menu, and really we're going to be looking at the unsupervised methods. Now, I can use clustering. So clustering will work pretty well on here. But one of the things I want to use, because this is such a complicated data set, is I'm going to use self-organizing maps. So, and I have done a self-organizing map description in about 1.5 minutes before. We might try and do an even quicker one now. But self-organizing maps is a way of letting the data self-organize itself so that self-similar data points sit close to each other and then get clustered close to each other. So you're looking at self-similarity across big chemical space in this case. What it does is you can imagine it a little bit like a football stadium. This is the analog I use. Think of a football stadium with a bunch of people stood in that football stadium. This is pre-social distancing. And they all have a certain hair color, they have a certain eye color, they have a certain height, weight. And what you're going to do is you're going to point to one person, you're going to say, right, go and move and stand next to the person around you that has the most similar attributes to you. And that person goes and does that. And then you're going to point to someone else and get them to do the same, point to someone else, get them to do the same. And you're going to iterate through and keep iterating through and do that. And slowly what you'll find is that football stadium of people will self-organize so that all the brown hair, blue-eyed, 6 foot, 70 kilo, 75 kilo people will all congregate in a certain place. And they'll be very different from the brown-haired, brown-eyed, 5 foot, 80 kilo people. Okay, and so this is a mechanism where the numbers themselves, the data itself, will self-organize and classify itself. So you're getting self-similarity. So that's what we're going to do here. We're going to do that now. I'm just going to do. Probably going to do. Actually, this is all logged. This is logged already. So this is already logged transformed, but just in terms of, I'm going to scale it from 0 to 1. I'm going to scale all the data just so that we don't get artificial effects from things with bigger numbers versus things with smaller numbers. So everything is equally weighted. I'm going to take the standard defaults. This is pretty well the way to do it in ioGAS. The standard defaults are the good place to start. And I'm going to learn. So we're going to chuck all the data in. It's chucking all of the data in the mix, and it's now going through that process of self-organizing that data. Now, this is a self-organizing maps are a type of neural network technique, and Dave talked about the human brain earlier. Neural network learning is the way that your brain actually works when it looks for patterns in the world. So this is a way of mathematically emulating the way the human brain would look for patterns in this data as well. So it just goes through. Be aware this is quite a slow technique. So if you've got a very big data set, there's 2 approaches. If you've got a very big data set, you can either sit there, hit the button and come back the next morning, or you can actually take a random subsample. And I think just in the data screen back up in here, there's a way of doing random subsamples of your data. this is a really good way of doing SOMs. If you've got a data set of 500,000 data points, a geophysical data set, for instance, and you want to do a SOM on it, take a random subsample of about 5%, do the SOM, train the SOM. If you're happy with it, save the SOM, and then apply the rest of the data back to the SOM, because applying the data to a pre-existing SOM is very quick. Learning the SOM or training the SOM is very slow. So there are ways of dealing with big data sets. So here's my SOM. So what am I looking at here? So I'm looking at a sort of a projection of my multi-dimensional data into 2D. These nodes have a set of samples on them. So this node here that I'm pointing at has 19 of my samples sitting on it. There's a node over here with none of my samples sit on it. And in each of these nodes, the different chemistries will adjust slightly. But what we find here is on the U matrix here, this is telling us about where those nodes are clustering. And what it is nodes that sit within a patch. This is like a topographic map. Think about it like that. Nodes in the valleys or basins are very similar to each other. So that all the nodes in this patch here are probably very, very self-similar in terms of how they behave chemically. But when you go across a ridge to another valley, these are very different. So these here are very different from these. So these are like ridges separating basins that have self-similarity. So think about it like a topographic map. And what we're going to do now is we're going to use a k-means classifier to then cluster out our nodes on this map so that we can then classify them relative to the SOM. So I'm just going to do that. We'll do that. So one of the things you can see here is it's a fairly drop. Now, that's a good point here. So with this, it actually is okay to kind of put a fairly high number in here. Run it again. You see a bit of variation here, you know, because really, as we generate more and more clusters, what we're doing here is we're breaking our U matrix up more and more into these little subdomains. So as we break it up into subdomains, we might be pulling out smaller and smaller groups. And there'll be an optimum point. So you may want to play with this a little bit. But what I'm looking at here is probably somewhere around, we'll try it around the 9 groups for now, which is again, you're a clumper or a splitter, right? But it's a reasonable set for something like this. So we're looking at 9 here. We're going to apply that. We're going to apply that to our color. So I'm just going to turn our densities off for a second. And we're going to apply this to our color groups. So there you go, that applies. So we've now broken those groups out. And you can see that, again, maybe we could have chosen more. So this is something you might want to look at. So maybe we could have chosen more clusters. See here, it's classified all of these as the same. So actually, you know what? I'm going to do that. Let's just do that. And I'll just go change the random seed randomly. Right, so we can see here that things really are flattening out. I'm going to just go beyond this point here and just choose 10, 11 or 12. You'll see what I mean. And now we saw at least broken that one out there. These are still classifying the same. So it's trying to find little populations. You can see there's a very distinct population here that is classified as red. There's a very distinct grouping of data. What you can do at this point is you can save the SOM. So you can save the SOM. That's where I said you can save this SOM, and then you can apply new data to it to classify the new data relative to this SOM. So what I'm going to do at this point is 2 things. I'm going to apply the SOM. So I'm going to apply it now to all of my data. Now, there's quite a bit of data here. This might take a few seconds to render on my screen. It is working on it. Because what it's doing is now going to apply those colors to all of these plots. So you can see it going there. It's now generated. There you go. So what that has now done is it's now applied those classifications to that data, and we can see now where those groupings sit in our XY plots. So we can see that there you go. There's that little red grouping there. It's a very distinctive group sitting there. Again, you as a human, Dave said, never stop thinking, right? You can look at this and you can say, oh, well, I might want to put that with that and I might want to pull that out separately. That's fine. Adjust it. It's just a way of giving you a starting position of how the data itself will cluster out. One of the other things you can do with a data set like this is you click the SOM weight map. And if on a complicated data set like this, what this shows you is it shows you on that U matrix, it shows you the contribution or the weighting of different elements to different parts of that U matrix. So if we look, for instance, at a potassium map here, we know that down in here, the groupings tend to be dominated by or have more of an influence of potassium, more of a weighting than up in here. And so if we look at iron versus potassium here, we can see that they are opposite. So we would tend to say, well, if this is lithology, our more sort of potassic lithologies don't tend to be sitting with our iron lithologies, right? And so you can start to use the SOM weight map to tell you what has fallen out in my SOM analysis. So here's some very distinctive chromes, chrome with iron up in here, but down in here is chrome without iron, right? That's something quite distinctive. And you may want to come back and try and break that out some more in the SOM analysis. So
and James,
yeah.
You can reality check yourself as well. With the CLR transform data, the maps are telling you that potassium goes with rubidium, as it should.
Yeah. Yep.
And so this is the thing, to feed back in your knowledge of process when you run something that's so mathematically quite obtuse. If you have potassium and rubidium not correlating on the SOM weight map, you'd go, well, what on earth is happening there? Why would that be the case?
Yep.
And you should question it. And you may have stuffed up the input data.
And I guess one of the other things to look for when you're running a SOM, and I didn't say it, is, when we look at this U matrix, look for structure. So if you see some nice ridges, some nice valleys, there is structure in the data. The data has been able to kind of pull itself apart quite nicely. If you look at the U matrix map with whatever data you're using, and it kind of looks uniform, it looks just a horrible mess, you can't see clear ridges, then there is less clarity to the SOM has done something less, you have got less clarity in your data, there's less clustering or less grouping.
Yeah, and that, James, that's it's a bit like right at the end of my talk at the start where I said sometimes from an exploration point of view, the hardest choice is to say there is no anomaly, basically walk away. Sometimes when you're hunting out structure in data, if that U matrix shows no pattern like that, then maybe there is no structure in the data, but think about the inputs. And a principal components analysis, if there's no correlation in input structure, then principal components won't do anything for you either. So it's trying to tell you that it's a schmozzle. There is no multivariate structure in the data. And sometimes that's the case.
So we've just gone through that. I won't bother saving this, but I've shown you how you can save it if you want to apply new data. So if you go through so this is 4 drill holes in a drilling program, or it could be a soil program. You generate your SOM at the start. You're happy with these classifications, you can save that SOM, and then new drilling data can come in and you can immediately classify it. So this is looking at it like this, but as Dave always pointed out, and we can look at it back in normal kind of ppm space like this, we've got those classifications. But what we've done, of course, is we have then generated clusters. We can label these if we want. But of course, and this is kind of brings it all home, I guess, is that we are looking at drilling data. So if we now just go and I'll just plot aluminium and iron and, I don't know, maybe I'll choose something crazy like, where are we? I thought copper might be in here somewhere, maybe not. Doesn't matter. Sulfur. Got 3 components there. I'm going to do a downhole plot, hole ID from 2, and select those 4 drill holes. And it plots those 3 components. And on the side here, we can see our SOM classification. So this is drill hole 1, 2, 3, and 4. Now, they're all scaled the same. You can see the depth labels are different. If we go over here, there's a thing saying common domain scales. If I just click that a couple of times, now we're plotting those drill holes in true space. You can see here we didn't start collecting data till lower down in drill hole. We don't know spatially where those drill holes are, but this is just a plotting as a fence line for now. But what you can immediately see is that there are places where there are color classifications that seem to be similar. There are things that look sort of, again, similar-ish, some oranges here that come in, orange to purple, orange to purple, orange to purple, kind of zone in here. So there are things that seem to be starting to hang together about replicating the sequence. This is actually drilling through a stratigraphic sequence in the Gawler Craton, actually. And we're actually in a rift environment here where the basalt flows are pinching and swelling. So there's a bit of complexity here. But what you can start to say is, well, okay, it looks like I've got something here. There's the same unit, yellow, yellow. It's got a purple unit on top here, but on here it's got an orange unit. On here it's got a brown unit. So you can start to then, this is where, and Dave pointed this out, and I'll point this out time and time again. Here's a tool. Here's something that tells you this is the way the data is falling out. Go and take this result, go and look at those rocks, go and look at the data some more, and now work out what's going on. But what you've immediately done is you've given yourself a really head start when you might be laying that core out and you've got data like this in your hand. It's telling you something about the structure of the core. It's telling you where there is major domains, where there are little subdomains sitting in a zone like this. These are actually little flow tops or flow domains sitting in a basalt flow, and we're pulling that out. And so you don't know that looking at the data, but you know that when you look at the data next to the rock. So this is where this is a tool for you. It's a tool to go and figure out what's going on. What is this red unit here, which is so distinctive? What is going on there? So I think that gives you a real sense for how that is used. I know, I guess, Dave, you did mention wavelet tessellation, didn't you? I'm going to have to think now how I can do that. I could do a wavelet tessellation in this.
In 2 minutes, James. Yeah.
In 2 minutes. Yes, I could. So what we could do actually is, yeah. Simply, you could just simply take something like iron. Right, this is the simplest thing you can do. Something like chemistry, iron. Right, you can plot that. If I plot that down hole, we can see the iron trace here. We can see it has domains in certain places. Is this going to fail? Maybe this might fail. Well, anyway, we'll give it a go. So I'm going to do the wavelet tessellation. Dave described it slightly. We'll do it on. I'll just do it on hole 1 for now, and I'm going to choose iron as my signal. So again, it doesn't matter what it is. It can be any downhole signal. It just has to be a consistent signal. And I'm going to hit OK, and there you go. There's a wavelet tessellation plotted for the iron in that data set. And I can just change that to showing the means. So I'm showing the log values there just to highlight the differences there. And so again, as a geologist, you might have that classification. You might have that wavelet tessellation. You can see boundaries here in my data, just from the chemical data. And I've laid that core out. I've got this data in my hand. I've done this analysis, and you've seen how quick I can do that. I thought about it. Now I'll go and look at the rocks, and I know I can now go, what does this mean for the rocks? How does this all tie together? So I think that's, look, I've gone through a lot quite rapidly there. Dave's been drinking. I haven't started yet, but that's not far off, I don't think. But I think what I hope I've shown you is some of the workflows and how we can build those more advanced analytics into workflows where we go from looking at the data like we did this morning to now starting to do advanced stuff like this to give us the tools we need to help us understand what's going on with our data. But never stop thinking. And it's always about using this in conjunction with your skills as a geologist, your skills in understanding process to work out what this means and how it helps you. Right, so now for those still around, I don't know whether people are. We've probably got a few minutes. So I wonder if my hosts here can help me. Right, there you go, chat. We've got a few minutes maybe to answer some questions, and we can do that. So Josh, Hugh, Matt, how do we want to do this?
Right, well, I'm looking at YouTube, and it looks as if all the questions that have been asked have been answered already, either by yourselves or in chats directly to the individuals.
Yep.
Unless
Okay.
anyone's got any more questions from the YouTube live stream, it's about 20-second delay, so we can definitely hold fire for that.
Okay, that's good. So
While you've been chatting, James, I've been answering some of the questions.
Okay, great. So what I will do is actually what I'm going to do, I'll just put this slide together, just so we have this on the screen while we're just talking for a few minutes. It's just how do you get hold of us? There's various methods. So people might have questions. Look, jump on our website, reflexnow.com. You can go to the ioGAS bit of that website. You can download a 2-week free trial of ioGAS. If you've never used it before, go and grab a 2-week free trial. There is demo data included in the ioGAS software. You don't even need to use your own data, but you can do. Go and play around with it for 2 weeks. You can learn about pricing and that kind of stuff on there. Send us a message from there. We'll get it.
So it's fully unencumbered, and if you're at a university, let us know.
Yep.
At a teaching institution of any sort, actually. We'll help you out.
Yep. Yeah, we can do that. We have a YouTube channel actually that we put informational videos on for all of our products and stuff, be it a survey tool, core orientation, to drilling optimization or drilling fluids to things in ioGAS. So there are some instructional videos on the YouTube channel for ioGAS. So we've got that. My email address is on there. I used a particularly fancy font just so that people wouldn't be able to see what it was. But honestly, reach out to us. We've got a LinkedIn channel as well that we do put stuff out on. Dave's based in Australia, in Perth. I'm based here in the UK. So you've got people in different time zones. We have geoscientists, actually, geoscience specialists based in North America. Gervais Perron would be one of the people that you might talk to there. Louis Farfan in South America, Nolene Pauls in Africa. So we have people around the place. Anyone can take a question, and if they don't know the answer, they know someone that does. So reach out to us. Pricing and stuff, best way, honestly, to get pricing requests is to go to the website, grab a free copy, just trial copy, fill out the form, and then get a pricing request that way, because that way we then coordinate getting a response to you as quick as we can. And yeah, for those using it, if technical questions you have, we're more than happy to hear them and hear what you're trying to do and help you out as best we can.
That's brilliant. Thanks very much, James. And like you say, I think what we'll do is try and capture the questions. So, if there's anything specific, you can follow up on those.
So there is a one there that Dave might want to just do in 30 seconds, which is what future developments do you have for the software?
Oh, well, there's a new version coming out, well, in the proverbial 2 weeks. James touched on some of the developments of that. But seriously, but that will have the live link into QGIS. Right. So one of the things we're looking at for the next release after that is using the multivariate tools, the more highfalutin tools in ioGAS. Everyone loves the data doctor, and really love the data doctor. It just makes things efficient. So we're looking at almost an AI type system to guide you into how to use the different, more complex analysis tools to suggest the best way to go. So it would sort of pre-look at your data and then say, maybe you should use this and do this to the data, and then guide you along that path, almost AI. That would be the analysis doctor, but shorten that at your peril if you're thinking of a name for it.
That's right.
Yeah, that's right. Yes, we're trying to work out what else to call it. Yeah. Anyway.
All right. Very quickly, gents. You've mentioned that there will be trial data inbuilt into the free ioGAS trial that you can download. I think one of the questions we've had is whether the data that you are using today, James, would be available as its own subset.
Good question. I've been using various data sets. Some are freer than others. So the soil data that we used at the start, probably not. The data we use with the dolomite control line, I would need to check on that. Let me get back to you. The data I just showed then with the self-organizing map, absolutely, that is data that you can download today from the South Australian Geological Survey. That is free data. That's from their mineral system drilling program. You can go and download that, all of that data. But we might find a way of actually making a leave that with me. I might find a way of making a sort of a cleaned version more available to people. So I just need to check on that. And what else have I used?
That's a good idea, James.
Yeah,
that's a good data set.
It's a good data set. It is a brilliant data set. And honestly, shows you the power that is portable XRF data. But portable XRF data done well with sample preparation, pucks, consistent and QA'd. And that's the results you can get from it. And some of the other stuff where there was your GOS and stuff. But I've got other data sets that we can use for. There are a few other ones. We've got the crab one I didn't show, Dave. But there are data sets like measurements of crab species and using that classifications of that. So there are data sets. Yeah, I think it's a good point. We probably haven't, as a group, looked long and hard at what new data sets we could provide to people for some of this stuff. So let us do that. The structural stuff. That structural data set, a subset of that or something similar is included in ioGAS now. So yeah, some and some. But yeah, leave that with us. We might look into that a bit more actually.
Awesome. And just to confirm, this is being recorded because I know a number of people have been asking if it's going to be uploaded subsequently.
Yeah, it's been recorded. Just whether James and Dave agree, if that's okay. Brilliant.
Yeah, it's all good. Absolutely. That's why we're here.
In that case, then we'll upload it to the Geoscience YouTube channel, and we'll also email all the participants with a link for that as well.
Yep.
Fantastic.
I think we were fairly well behaved.
Excellent. And hopefully we can follow up with a more in-person training course at some stage when COVID restrictions allow.
Yeah, so I think the other thing I'll just put out to the audience online is, look, keen to hear from people what they want, what they are looking for. It's something we've been kind of thinking about, I guess, a fair bit, Dave. I think that's right. And there's a few people out there running ioGAS related training, but let us know whether you want training, what kind of training, face to face, 5 days, 1 day, online. Let us know your thoughts because we are thinking about how we manage that, be it ourselves or with someone else involved.
Excellent.
Okay, that's fantastic.
Come in or
nothing else in from YouTube.
A few good comments here, so that's good.
Okay, then in that case we'll wrap up. But no, thanks very much, James and Dave. Thanks for staying on.
Yep.
Really enjoyed it.
Yeah, thanks. Well, thanks for hosting, and thanks for everyone for sitting in and listening. And thanks for Dave for taking the wrong end of the day for this one.
I think it's the right end of the day, actually.
Excellent. All right. Thanks very much, everyone.
Thanks very much.
Thank you very much.
Yes.
Adios. Ciao.